Night after night, wide-field sky surveys operate with a patient rhythm that is built for discovery. A survey telescope aims at a planned region of sky, records a brief exposure, then shifts to the next field and repeats. The purpose is not to admire a single object, but to compare the sky with itself again and again until a change appears. In a single image, most points of light remain fixed in place relative to one another. Stars sit in patterns that do not move from one minute to the next. Galaxies appear as faint smudges that also hold their positions. A moving object reveals itself only when the same field is observed more than once, separated by minutes or hours, and the images are placed side by side. In that comparison, a small point that shifts against the star background becomes a candidate. This is the first moment when an object later called Three-Eye Atlas enters human attention, not as a body with a story, but as a deviation from stillness. The discovery begins in a stream of images, not in a single dramatic frame. Each exposure contains noise defects and distractions. Cosmic rays strike the detector and leave bright streaks that exist only in one image. Satellites cross the field and draw thin lines. Aircraft lights can appear as dotted trails. Detector pixels can be unusually bright or unusually dim, and those fixed flaws can mimic or hide faint points of light. The first work of discovery is therefore a work of sorting in which software and careful review distinguish what belongs to the sky from what belongs to the instrument. In modern surveys, software searches for transient points by subtracting a reference image of the same field taken earlier under similar conditions. What remains after subtraction is a map of changes. Most changes are not new celestial bodies at all. They are small shifts in focus differences in atmospheric clarity or variations in background glow. A true moving object is identified through persistence across multiple frames in a way that matches the expected appearance of a point source. The candidate appears at one location in one exposure, then at a slightly different location in the next, with the change consistent with a steady drift. At this early stage, the object is not yet a comet, not yet an asteroid, not yet anything more than a moving point. It is a track drawn in discrete steps. The survey system assigns it an internal identifier and reports it to a central clearinghouse where observations are collected from many observatories. The report is not a narrative. It is a compact set of measurements. Timestamps, sky positions, brightness estimates, and details about the instrument and filter used. Even the timestamps are treated with care, because the motion of the object must be tied precisely to Earth's rotation and orbit. The telescope's location on Earth matters. The exact moment each exposure begins and ends matters. When an object is far away and moving slowly, a small timing error can still shift the inferred path enough to matter later. Discovery reports therefore include standardized time references and observatory codes so that other teams can interpret the measurements correctly. If the moving point is faint, the first report may contain only a few detections, perhaps 2 or 3 in one night, and perhaps one more on a second night. That is enough to know it moves, but not enough to know where it is headed. At this stage, the object sits close to the threshold of the survey's sensitivity. The atmosphere blurs it. The background sky brightens it. The stars around it can contaminate its measurement. A point too close to a bright star may be missed entirely, because the star's glare dominates the subtraction image. A point near a galaxy may be mismeasured because the galaxy's diffuse light changes the local background. A point near the edge of the detector may be distorted by optics. The survey's first task is to obtain a clean set of repeated detections that show the point's consistent motion. If the candidate survives automated checks, it becomes a target for follow-up. Follow-up begins as a search for recovery. Another telescope, sometimes the same survey, and sometimes a different observatory, returns to the reported region of sky at a predicted time. The prediction is crude. With only a short arc of observations, the candidate's future position can be uncertain by a large patch of sky. Recovery teams therefore search within that patch, looking for the same moving point. A successful recovery adds a new position and time, which shrinks the uncertainty and strengthens the case that the detections belong to a single object rather than coincidental noise. In the earliest stage, the motion can be measured only as a shift on the sky, a change in angle relative to the stars. The actual distance of the object is not yet known with confidence, so the same apparent shift could correspond to different real speeds depending on how far away the object is. This is why early discovery is cautious and procedural. The system does not assume a dramatic interpretation. It assumes that faint things can fool the eye and the algorithm, and that repeated observation is the cure. The process also includes human review. Even with advanced software, survey pipelines produce false candidates. Experienced reviewers learn the signature of detector defects, the look of subtraction artifacts, and the typical shapes of satellite trails. A true moving point has a star-like profile shaped by atmospheric blurring, and it shifts in a way that is consistent across exposures. Reviewers check whether the candidate sits on the same detector pixels each time, which would suggest a fixed defect rather than a moving object. They check whether the candidate aligns with a known satellite track. They check whether the candidate appears in images taken with different instruments or at different sites, which would make an instrument-specific artifact unlikely. When the candidate passes these checks, it enters the catalog of real moving objects still unnamed in any familiar sense, but now part of a shared observational record. If the object later receives a designation like 3I Atlas, that designation reflects this institutional pathway. It encodes discovery circumstances and cataloging conventions rather than physical nature. The designation does not claim that the object is unusual or ordinary. It states that the object exists, that it moves, and that it has been measured. In the same early phase, brightness is recorded in a standardized way. Brightness in an astronomical image is a count of detected light within an aperture corrected for background. It is affected by atmospheric clarity, by the altitude of the object above the horizon, and by the sensitivity of the detector. Surveys calibrate brightness using stars of known brightness in the same field, translating detector counts into a comparable scale. For a faint moving object, that calibration can be uncertain because small differences in background subtraction can change the measured value. Still, a rough brightness estimate is useful because it helps plan follow-up. A very faint object may require a larger telescope to recover. A somewhat brighter object may be followed by a wider network. Discovery also depends on cadence, the planned pattern of revisiting the same region of sky. A survey designed for near-Earth object detection revisits fields on timescales that are suited to objects that move noticeably in hours. An object moving more slowly can be overlooked if the cadence is not matched to its drift, because it may be confused with fixed sources. Some surveys compensate by linking detections across longer intervals, searching for consistent motion across multiple nights. This linking is computationally demanding because the number of possible combinations grows quickly. The pipeline must decide which points in one image correspond to which points in another across a sky crowded with stars and galaxies. The success of discovery depends on careful thresholds, not too strict to miss real objects and not too loose to drown in false tracks. Within this machinery, Three-Eye Atlas becomes visible when its motion and brightness align with what the survey is designed to detect. It is not singled out by an extraordinary appearance at first sight. It is singled out by persistence across exposures and by a motion that can be linked into a track. The first discovery record is therefore a small set of time-stamped positions, each one a careful estimate derived from pixels and star catalogs, each one an anchor in a growing chain. What exists at this stage is not yet a deep understanding, but a disciplined noticing. The sky is observed as a steady background, and the object is identified as a controlled exception to that background. The discovery is a transition from anonymity to traceability. From that point onward, the object can be sought again, measured again, and tested again against the predictable geometry of the sky as Earth turns and moves through space. The first section ends here, still at the widest observational layer, where the essential act is repeated measurement and the careful separation of motion from illusion. Once a moving point is flagged and recovered, the next layer of work narrows from wide survey context to the specific act of measuring position. That act is called astrometry, a practice that turns a faint spot on a detector into a pair of sky coordinates tied to a time. The measurement begins with the raw image, which is a grid of pixels, each pixel holding a count of detected light. The moving object usually appears as a small blur shaped by the atmosphere and the telescope optics. Even in good conditions, the object is not a perfect point. Air turbulence spreads starlight into a pattern called the point spread function, which has a bright core and a fading halo. The object's measured position depends on how that pattern falls across neighboring pixels. If the object is bright, the center can be found with high precision by fitting a mathematical profile to the pixel values. If the object is faint, the profile fit becomes uncertain because noise from the sky background and detector electronics competes with the object's signal. The goal is to estimate the centroid, the best estimate of the object's center of light. For a faint moving object, the centroid can shift depending on the choice of aperture and the local background estimate. These are not philosophical uncertainties. They are concrete differences that arise from pixel statistics. The image must first be calibrated. Calibration removes detector bias, which is an artificial baseline signal present even with no light. It removes dark current, which is a slow accumulation of charge caused by thermal effects in the detector. It corrects for flat field variations where some pixels are slightly more sensitive than others. Without these steps, the brightness pattern of a faint object could be distorted, and the centroid estimate would be biased. After calibration, the image is mapped to the sky using reference stars. This mapping is called an astrometric solution. The telescope's optics introduce distortions that make the mapping from pixel coordinates to sky coordinates slightly non-linear, especially near the edges of the field. Atmospheric refraction also shifts apparent positions, bending light toward the zenith, with the effect increasing at lower altitudes. The astrometric solution accounts for these influences by matching many stars in the image to stars in a catalog. Modern catalogs provide precise positions for vast numbers of stars, along with their proper motions, which are the slow drifts of stars across the sky over years. Proper motion matters because a reference star's position today is not exactly the position recorded decades ago. A good catalog predicts where the star should be at the time of observation. The matching process uses many stars across the field to solve for the transformation that best aligns the image with the catalog. When the solution is good, the residuals, which are the differences between measured star positions and catalog positions, are small and show no systematic pattern. If residuals grow toward the edges, that suggests uncorrected optical distortion. If residuals shift uniformly, that suggests a timing or pointing offset. This is why astrometry is both local and global. The object's position depends on how the entire field is anchored. Timing is the next essential ingredient. A sky position without a correct timestamp is not useful for orbit fitting. Observatories record exposure, start times, and durations using synchronized clocks. The time standard is typically coordinated universal time. The time is often expressed in a format that is precise to fractions of a second. Even if the object's sky motion is slow, timing errors can accumulate when combined with multiple observations and with Earth's own motion. Earth rotates, so the observatory's position changes as the night progresses. Earth orbits the Sun, so the viewing geometry changes from night to night. A correct timestamp ensures that the measured sky position can be transformed into a line of sight from a known point in space. The observatory's location, given by latitude, longitude, and altitude, matters for this transformation. Two observatories separated by thousands of kilometers will see the same object against slightly different star backgrounds, an effect called parallax. Parallax is small for distant objects, but it is not zero, and it can be valuable. When the object is close enough, parallax between observatories helps constrain its distance. When the object is very far, parallax is tiny and harder to use, but accurate observatory positions still matter for consistency. The practical astrometric measurement of the moving object uses the field solution to convert the object's pixel centroid into a right ascension and declination, the standard sky coordinates. Right ascension is like longitude on the sky measured along the celestial equator. Declination is like latitude measured north or south of the celestial equator. These coordinates are tied to a reference frame that is defined by distant extragalactic sources, making it stable. Each measurement also includes an estimated uncertainty. That uncertainty reflects the scatter expected from centroiding error, catalog error, and the residuals of the astrometric solution. For a faint object, uncertainty can be dominated by centroiding. For a crowded field with few suitable reference stars, uncertainty can be dominated by the field solution. For low-altitude observations through thick atmosphere, refraction and seeing can worsen both. A careful team also checks for systematic biases. One common bias arises from trailing. If the object moves appreciably during the exposure, its image elongates. The centroid of an elongated trail depends on the direction of motion and the exposure timing. In a long exposure, the object's recorded light is a blend of its positions over the exposure duration. The effective time for the centroid is then close to the mid-exposure time, but if the object brightens or fades during the exposure, or if the trail is uneven because of tracking issues, the centroid can shift. Some observations therefore use shorter exposures to reduce trailing. Others deliberately track at the object's rate so stars trail while the object remains point-like. That strategy changes the astrometric problem because the reference stars are no longer point sources and must be measured differently. Another source of bias is background contamination. If the object lies on top of a faint galaxy or near a star, the background is not flat. Subtracting a local background can remove part of the object's light or leave residual gradients that pull the centroid. Some teams use image subtraction against a deep reference image to remove static background sources, improving the centroid. The important point is that astrometry is not just reading coordinates from an image. It is a chain of controlled transformations, each one with assumptions and error budgets. When many such measurements are gathered over nights, they form a set of time-tagged directions from Earth to the object. In this layer of the work, the object is still just a moving point, but now it is a moving point pinned to a precise coordinate grid. This pinning is what makes later claims possible, because any later statement about unusual motion acceleration or responsiveness must first pass through this measurement pipeline. If the pipeline is unstable, the later inference is unstable. If the pipeline is disciplined, the later inference can be tested. As the observations continue, analysts look at the residuals between the measured positions and the positions predicted by a provisional orbit. A pattern in residuals can reveal a problem. Residuals that oscillate with a daily period can suggest a timing issue or a systematic astrometric error tied to the telescope pointing. Residuals that grow as the object approaches the horizon can suggest unmodeled refraction or poorer seeing. Residuals that align with the direction of motion can suggest trailing effects. By diagnosing these patterns, teams refine their measurements, reject low-quality points, and improve the reliability of the dataset. In this way, the second observational layer establishes the foundation, a set of positions with known uncertainties derived from calibrated images anchored to a star catalog and stamped in time. Only after this foundation is firm can the next layer convert apparent motion into a trajectory. For now, the focus remains on the practical act of measuring where the object is precisely enough that the sky itself can be used as a ruler. With a growing set of astrometric positions in hand, the next step remains in the same outer observational region, but moves inward from raw measurement to the geometry of motion on the sky. The data points are still angles and times, not yet a full three-dimensional path. Each observation provides a direction from Earth toward the object at a specific moment. On the celestial sphere, those directions trace a line that can curve, speed up, slow down, or even appear to loop depending on viewing geometry. The apparent motion is a blend of the object's true motion through space and Earth's own motion as an observer. Earth rotates once every day, carrying the observatory in a circle. Earth orbits the Sun once each year, shifting the viewpoint by millions of kilometers. The observed track is therefore not a pure signature of the object alone. it is a signature of relative motion. Understanding this is essential because a pattern that looks like a response can emerge naturally from changing geometry. The first description of motion is often expressed as rates of change in right ascension and declination over time. Over a short interval, the motion can be approximated as linear. The object shifts a small amount east or west and north or south each hour. The rates can be computed by fitting a line to the measured coordinates across several exposures. If the object is near the celestial equator, right ascension changes map cleanly to angular movement, but the conversion depends on declination because lines of right ascension converge toward the poles. Analysts often convert the motion into a vector on the sky in arcseconds per hour, an angular speed. This is still an apparent speed, not a physical speed. Two objects with the same angular speed can have very different real speeds if they are at different distances. A nearby object can sweep quickly across the sky, even with a modest real velocity, while a distant object can appear nearly fixed, even if its real velocity is large. Distance is the missing piece, and at this stage, distance is only weakly constrained. Nonetheless, the sky motion contains clues. One of the most important clues is curvature. If the object's apparent track curves over days, that curvature can arise from the object's changing direction in space from Earth's orbital motion, altering the line of sight, or from a combination of both. Earth's orbital motion produces an effect similar to parallax on a grand scale. As Earth moves along its orbit, the viewing angle changes and a nearby object appears to shift against the distant star background more than a distant object does. This annual parallax component can imprint a gentle curve in the track that depends on the object's distance and the season of observation. Even without a direct distance measurement, the pattern can help constrain possible orbits. Another key geometric effect is diurnal parallax. Because an observatory is not at Earth's center, but on its surface, Earth's rotation moves the observatory by thousands of kilometers during a night. For nearby objects, this can shift the apparent position enough to measure. For distant objects, it is tiny, but it still exists. When data from multiple observatories at different longitudes and latitudes are combined, their different perspectives can slightly spread the measured positions. If that spread is consistent with expected parallax and measurement uncertainty, it strengthens confidence in the dataset. If the spread is larger than expected, it can indicate underestimated errors or subtle biases in different instruments. The sky track is also influenced by the choice of coordinate frame. Right ascension and declination are fixed relative to distant space, but Earth-based observations are made in a rotating frame. Some analyses transform observations into topocentric coordinates, which are centered at the observatory, while others transform into geocentric coordinates, which are centered at Earth's center. The transformation corrects for the observatory's position and makes the dataset more consistent. Further transformations can reference the barycenter of the solar system, the center of mass around which the planets orbit. These choices matter because small differences in reference point change the inferred path when precision is high. At this stage, the practical question is how to interpret changes in the apparent motion. A moving object may appear to accelerate on the sky, meaning its angular speed increases. That can happen if it is approaching Earth, because the same real speed produces a larger angular shift when distance decreases. It can also happen if it is approaching the sun and speeding up under gravity, which increases its real speed. It can also happen if Earth's motion changes the relative geometry so that more of the object's velocity projects onto the plane of the sky. In the opposite direction, an object can appear to slow down or even reverse its motion on the sky. This is common for planets which sometimes show retrograde motion when Earth overtakes them in orbit. A small body can also show apparent retrograde motion depending on its orbit and Earth's position. None of these effects require any unusual force. They are consequences of relative motion and projection. The apparent path can also shift in a way that looks like a bend or kink if the observations are sparse. If there is a gap of several days without data, the object's predicted position may be uncertain, and the next recovery may land slightly off the earlier linear extrapolation. When the new point is connected to the old points, the track can look like it changes direction. In reality, the true track may have been smoothly curving all along, but the sampling has been too coarse to reveal it. This is why survey cadence and follow-up density matter. The object is not observed continuously. It is sampled at discrete times, and the human mind is tempted to connect samples with straight segments. A careful analysis instead fits a continuous model and checks residuals rather than trusting visual impressions. Measurement errors also contribute. Each astrometric point has uncertainty. If the uncertainty is, for example, a fraction of an arcsecond, then a small shift in the measured positions can slightly rotate the inferred motion vector. Over multiple nights, these small rotations can create the impression of jitter. If the dataset includes points from different telescopes with different systematics, the jitter can increase. The correct response is not to treat the jitter as physical behavior, but to quantify it and see whether it exceeds expectations from measurement errors. Analysts use statistical methods to assess whether observed deviations from a simple model are significant. They do this by comparing the residuals to the uncertainties. If the residuals are comparable to the uncertainties, the model may be adequate. If the residuals are systematically larger, the model may be missing a physical effect, or the uncertainties may be underestimated. In the sky geometry layer, another subtle factor is light travel time. The object is not seen as it is at the moment of observation, but as it was when the light left it. For solar system distances, this time delay ranges from minutes to hours. For orbit determination, the time delay can be accounted for ensuring that the object's modeled position corresponds to the emitted light time. This correction is small but important for precision. It is another way in which the simple idea of watching an object move must be refined into a measured procedure. As the track grows, analysts may describe it in terms of great circle motion, the path a moving point would trace on a sphere if it moved in a straight line through space at constant velocity relative to Earth. Deviations from a great circle indicate acceleration or changing geometry. But because Earth itself accelerates in orbit, the great circle concept is only approximate. A better approach is to move toward orbit fitting, but the geometric analysis still plays a role. It guides where to look next for recovery. It informs how large the search region should be. It reveals whether the object's apparent motion is consistent with a nearby fast mover or a distant, slow mover. This matters because different physical classes of objects tend to occupy different distance and speed regimes. A near-Earth asteroid moves rapidly across the sky and changes position noticeably within an hour. A distant comet far beyond Mars moves slowly and may require multiple nights to see a clear drift. An interstellar object, if truly on a hyperbolic path through the solar system, can have distinctive motion patterns, but those patterns still emerge through geometry and relative motion, not through immediate interpretation. In this section, the emphasis remains on disciplined translation. The sky provides angular changes. The task is to interpret those changes as projections of a three-dimensional path, while respecting what is unknown. The moving point called 3I Atlas is not yet assigned a motive. It is assigned a vector and a curve, each derived from timed angles, each shaped by the observer's own motion. The appearance of responsiveness is not addressed yet, because the correct order is to understand how an ordinary trajectory can look irregular when viewed from a moving platform on a rotating planet. The work proceeds by converting a sequence of sky positions into a coherent description of apparent motion and by preparing the dataset for the next layer where a preliminary orbit can be fit and tested against the measurements. With measured positions and a careful description of apparent motion, the analysis moves one step inward from geometry on the sky to the first attempt at a physical path through space. This step is the first orbit solution. It is called a solution because it solves a specific problem. Find the set of orbital parameters that best reproduces the observed directions at the observed times, given the gravitational influence of the Sun and, when needed, the major planets. The solution is not a declaration of certainty. It is a model that is tested against data. At the start, the data arc is short. A short arc means the object has been observed over a limited time span, perhaps a night, perhaps several nights. With a short arc, many different three-dimensional trajectories can project to similar apparent motion on the sky. This is why the first orbit is provisional. It is an entry point into a space of possibilities, not an endpoint. The orbit determination begins by treating each observation as a line of sight. From Earth at a known location at a known time, the object lies somewhere along that line. The missing information is the distance along the line at each time. If distance were known, the object's three-dimensional position would be known, and velocity could be inferred from changes in position. Without distance, analysts must infer both position and velocity by finding an orbit that makes the lines of sight intersect a single moving object path. Early algorithms use classical methods developed for this exact purpose. They take three observations at three times and solve for an orbit that passes through them under the assumption that the object follows a Keplerian trajectory around the Sun. A Keplerian trajectory is an orbit defined by gravity alone with the Sun as the dominant mass. In reality, planets perturb orbits, but the first step often uses a simplified model and then adds perturbations later. The classical methods produce an initial guess, a preliminary orbit that can be refined. Refinement is iterative. The model predicts where the object should appear on the sky at each observation time. Those predicted positions are compared to the measured positions. The differences are residuals. The algorithm adjusts the orbit parameters to reduce residuals, seeking the best fit within the uncertainty of the measurements. This process is a form of least squares fitting. Each observation can be weighted according to its estimated uncertainty, so that high-precision points influence the fit more than low-precision points. This weighting is important when the dataset includes measurements from multiple telescopes with different noise levels. The outcome of the refinement is a set of orbital elements parameters that describe the shape and orientation of the orbit and the object's position along it at a given time. These elements include the size of the orbit, often expressed as a semi-major axis for bound orbits, or an equivalent parameter for unbound trajectories. They include eccentricity, which describes how stretched the orbit is. Eccentricity less than 1 indicates an ellipse, a bound orbit. Eccentricity equal to 1 indicates a parabola, a limiting case often used as an approximation for comets on long-period orbits. Eccentricity greater than 1 indicates a hyperbola, an unbound trajectory, which is the signature of an interstellar visitor passing through the solar system. The elements also include inclination, which describes how tilted the orbit is relative to Earth's orbital plane, and other angles that define the orientation in space. The first orbit solution can therefore hint at whether the object is likely bound or unbound, but it cannot yet prove it with high confidence if the arc is short. Small changes in measured positions can shift the eccentricity estimate, especially when the object is far from the Sun and moving slowly. In that regime, the difference between a very elongated bound orbit and a slightly unbound orbit can be subtle in the observations. This is why analysts report uncertainty ranges and consider alternative fits. The early orbit can also be affected by assumptions about planetary perturbations. If the object passes near a planet, or if the observation arc covers a time when Earth's own motion changes rapidly. Relative to the object, the influence of planets on the apparent motion can be significant. A preliminary orbit that ignores planetary effects can misattribute a small deviation to the wrong parameter, leading to a biased eccentricity. Therefore, more complete orbit solutions incorporate the positions of the planets and integrate the object's motion under their combined gravity. Even then, there's a distinction between heliocentric and barycentric orbits. A heliocentric orbit is referenced to the Sun's center. A barycentric orbit is referenced to the solar system's center of mass. For objects at large distances, barycentric elements are often more stable for classification because the Sun itself moves around the barycenter due to planetary gravity. A small shift in reference frame can change the computed eccentricity slightly. Careful analysis distinguishes these frames to avoid overinterpreting a marginal value. The first orbit solution produces not only a best fit orbit, but also a covariance, a mathematical summary of uncertainty and correlation among parameters. The covariance expresses which combinations of parameters are tightly constrained by the data and which are not. Often with a short arc distance and velocity along the line of sight, are weakly constrained, leading to strong correlations. This means that a change in one parameter can be compensated by a change in another and still fit the data nearly as well. In practical terms, this creates an uncertainty region on the sky for future positions. That region can be elongated, reflecting the fact that some directions of error grow faster than others. Recovery predictions are therefore made with an uncertainty ellipse rather than a single point. The size of this ellipse can be large at first, shrinking as more observations are added. The first orbit solution is also tested for plausibility. Analysts check whether the orbit implies an unrealistically close approach to Earth that would have made the object brighter. They check whether the orbit implies a path through regions of the sky where the object would have been visible earlier in archival survey images. They check whether the orbit matches any known object that might have been previously observed and then lost. This is because the same physical object can be rediscovered under a new provisional designation if its earlier observations were not linked. Linking a new track to older detections can greatly extend the arc and improve the orbit. This is called precovery, when earlier images contain the object unknowingly. Precovery is powerful because it can turn days of data into months or years of data, transforming uncertainty into constraint. In the early stage, teams search archival images near the predicted past positions. If the object is found, its earlier positions are added and the orbit is refit. If it is not found, that absence still provides information because it can rule out trajectories that would have placed the object in a visible region at a visible brightness. For an object like 3I Atlas, the first orbit solution sets the baseline for later discussion, claims that the object changes trajectory, accelerates unexpectedly, or appears to respond to something must be evaluated relative to a gravitational model. But at this stage, the model itself is still being built. The correct interpretation of the first orbit is therefore cautious. It is a best fit under certain assumptions with limited data. It is used to predict where to look next. It is used to plan observations with larger telescopes or different instruments. It is used to decide whether the object is likely a comet, an asteroid, or an interstellar visitor. It is not used to assign intention. The orbit solution is also sensitive to the quality of the astrometric measurements. A single outlier point with a large error can pull the fit. Analysts therefore screen the data set, removing points that are clearly inconsistent or that have poor conditions. They may also rerun the fit with different subsets to see how stable the parameters are. If the eccentricity changes significantly when one or two points are removed, the orbit is not yet robust. If the eccentricity remains stable across reasonable subsets, confidence grows. In this way, the first orbit solution is a living estimate updated as data arrives. It is an inward step because it leaves behind the pure sky plane description and commits to a three-dimensional physical path, even if that commitment is provisional and surrounded by uncertainty. The moving point becomes a trajectory in space defined by parameters that can be compared, refined, and tested. After a first orbit is obtained, the analysis remains in the same overall observational layer, but moves inward toward a disciplined treatment of uncertainty and the existence of rival paths. The early orbit fit provides a best estimate, yet it also provides a warning. Many solutions can be compatible with the same data when the arc is short and the measurements carry noise. In this stage, uncertainty is not an afterthought. It becomes a primary object of study. The main question is not only which orbit fits best, but how strongly the data prefer it over nearby alternatives. Orbit parameters are not independent knobs. They are linked. For example, a slightly different assumed distance at one time can be compensated by a slightly different velocity along the line of sight, still producing nearly the same apparent motion. The covariance matrix produced by a least squares fit captures this linkage. It encodes the idea that errors tend to lie along certain directions in parameter space rather than spreading evenly. This is why uncertainty regions are often elongated. They represent combinations of parameters that can vary together while leaving the predicted sky positions nearly unchanged over the current arc. Analysts interpret this by generating a cloud of possible orbits consistent with the measurements and their uncertainties. One common approach is to sample the uncertainty distribution and propagate each sampled orbit forward in time. Each orbit produces a predicted future sky position. The result is not a single predicted point, but a distribution of possible points. In the early stage, this distribution can stretch into a long track on the sky, because the main uncertainty often lies in how far along the orbit the object is, which translates to timing differences along its path. This long track is sometimes called the line of variation. It is the practical guide for recovery. Observers search along this region because that is where the object most likely will be, even if the best fit orbit places it at one particular spot. The same uncertainty propagation can be run backward in time. That backward propagation is used to search for precovery images. It also clarifies how the object might have moved through the inner solar system before discovery within the range of possibilities allowed by the data. This backward view can reveal rival interpretations. A dataset may permit a family of bound orbits and a family of unbound orbits both consistent within error bars. It may permit both a slightly more inclined orbit and a slightly less inclined orbit. The existence of rival paths is therefore a normal feature of early orbit determination. The key is to quantify how rival they truly are. Analysts look at metrics such as the root mean square residual, the average size of the differences between observed and predicted positions. If two different orbits yield similar residuals, the data do not yet distinguish them. Analysts also check whether residuals show systematic trends. A model that yields small residuals but with a consistent drift in one direction may be missing a physical effect, whereas a model with slightly larger residuals but no trend may be more realistic given measurement uncertainties. In addition, the weighting of observations matters. If uncertainties are underestimated for a set of points, those points can dominate the fit and create a false sense of precision. A careful analysis may inflate uncertainties to account for systematic errors, producing more realistic uncertainty regions. This practice is sometimes called debiasing or reweighting, and it recognizes that measurement errors are not always purely random. Systematics can come from star catalog errors that vary across the sky, from optical distortion that is not perfectly modeled, or from background contamination that shifts centroids in a direction correlated with local star density. To understand uncertainty, analysts also consider how the observation arc relates to the object's distance. For a distant object, the apparent motion is slow and the curvature of the track is subtle. Over a short arc, the track can look nearly linear. In that case, the line of sight distance is poorly constrained because many distances can produce similar angular motion with suitable velocities. This is why distant objects can have large uncertainty in their heliocentric distance early on. For a nearer object, parallax and changing geometry across a night can help constrain distance more quickly. Therefore, the same number of observations can yield very different constraint quality depending on where the object is. Another contributor is the distribution of observation times. Observations clustered within a single night constrain short-term motion well, but may not constrain curvature or acceleration due to gravity over longer intervals. Observations spread across multiple nights, especially with varying viewing angles, constrain the orbit more strongly. This is why follow-up campaigns aim to extend the arc as quickly as possible. A single additional night can shrink the uncertainty region dramatically because it adds information about how the motion evolves. Rival paths can also arise from data association, the question of which detections belong to the same object. In crowded survey data, it is possible for a detection in one night to be incorrectly linked to a track from another night, creating a spurious orbit. Most pipelines have checks to reduce this risk, but when objects are faint and near the detection threshold, the chance of misassociation increases. Analysts therefore verify that the linked detections produce a coherent orbit, and that removing one detection does not entirely change the fit. They may also look at the images themselves to confirm that each detection has the correct point-like shape and is not an artifact. If a dataset includes a few marginal detections, rival paths can reflect whether those detections are real. A robust orbit is one that remains similar when marginal points are down-weighted or removed. In the context of a provocative claim, such as an object responding to something, this stage is crucial because it separates true physical deviations from the normal flexibility of early fits. A claim of a trajectory change must be evaluated against the full uncertainty envelope of the predicted path. If the new measurements still fall within the envelope of plausible gravitational orbits, then the apparent change can be explained by the earlier uncertainty, not by new forces. This does not dismiss the possibility of additional forces. It simply keeps the logic ordered. First, the data must be shown to lie outside the range of gravitational predictions given realistic errors. Only then does it make sense to consider non-gravitational effects. This is why uncertainty analysis is sometimes more important than the best fit orbit itself. It sets the threshold for surprise. A second aspect of rival paths appears when considering the influence of planets and the reference frame used to describe the orbit. An orbit described in a heliocentric frame at one moment can shift slightly when converted to a barycentric frame, especially for objects far from the Sun. The eccentricity, which is often used to classify an object as bound or unbound, can differ slightly between frames. For an object near the boundary where eccentricity is close to 1, this difference can matter. Analysts therefore report both and emphasize the uncertainty. They may also compute the inbound barycentric velocity, which is a more stable indicator of whether the object is interstellar. Even then, a short arc can leave this velocity uncertain. Rival paths can therefore include both an interstellar interpretation and a long-period comet interpretation until the arc grows. The practical output of this stage is a better defined search strategy and a clearer sense of what the data truly constrain. Observers use the uncertainty region to point telescopes for recovery. They plan cadence to maximize constraint, such as observing at times when the object's predicted motion relative to Earth changes most, because that provides leverage on distance. Analysts monitor how the uncertainty shrinks with each new observation. They look for a transition where the orbit becomes stable, meaning that adding new data makes only small changes to the parameters. When that stability is reached, rival paths collapse into a narrower family, and classification becomes more reliable. Until then, caution is not a stylistic choice. It is a requirement imposed by geometry noise and the structure of the orbit-fitting problem. The object remains a moving point with an evolving predicted future, and the honest description is a range of futures rather than a single one. In this section, the work stays close to the measurable, treating uncertainty as an explicit part of the description and recognizing that early data naturally allow multiple trajectories that appear different but are not yet distinguishable. As the observation campaign continues, the focus moves inward from uncertainty itself to the practical process of extending the observation arc and tightening orbital parameters. The arc is the span of time over which the object is observed. Extending it is not simply adding more points. It is adding points that change the geometry of the problem, points that provide leverage on distance curvature and the influence of gravity. Early on, the object's predicted position may be uncertain across a wide area. Recovery observations are planned using that uncertainty region, and successful recoveries shrink it. Each new measurement is compared to the predictions from the current best fit orbit. If the measurement lies close to the prediction, the orbit is reinforced. If it lies offset, the orbit is updated. Either outcome is useful because the orbit is refined by the new information. In practice, observers aim for frequent updates because the predicted uncertainty can grow with time. If an object is not observed for too long, the uncertainty region can expand until recovery becomes difficult, especially for faint objects near the detection threshold. This is why follow-up networks respond quickly. They share ephemerides' predicted sky positions with uncertainties so that telescopes around the world can point efficiently. Recovery efforts also account for the object's brightness and observing conditions. A faint object can be lost in moonlight in twilight or in poor atmospheric seeing. It can also be lost when it passes through dense star fields near the Milky Way, where background confusion increases. Observers therefore plan around the lunar cycle and around the object's sky path. A recovered object is tracked not only for position, but also for brightness and morphology, because changes in brightness can affect measurement quality. A brightening object can be measured more precisely. A fading object can become marginal, increasing centroid uncertainty. Morphology matters because a point-like object yields a clean centroid, while an object with a diffuse coma yields a less well-defined center. The astrometric method may shift from centroiding on a sharp profile to fitting a broader profile, and different teams may adopt different conventions. To keep the dataset consistent, analysts may choose to use only measurements from teams that follow certain standards, or they may incorporate larger uncertainties for measurements likely affected by coma. The act of tightening orbital parameters is therefore both observational and statistical. On the observational side, teams improve calibration. They use updated star catalogs, better models of optical distortion, and more careful background subtraction. They take multiple exposures in a night to average out random noise. They observe at higher altitude angles when possible to reduce atmospheric refraction and distortion. They choose filters that optimize signal-to-noise for the object's spectrum and the sky background. On the statistical side, orbit fitters update weights, reject outliers, and monitor residual patterns. They may apply debiasing corrections that account for catalog systematics. They also incorporate planetary perturbations more carefully as the orbit becomes better defined. This is especially important if the object's path brings it near a planet, or if the time span includes enough motion for small perturbations to matter. As the arc grows from days to weeks, the object's apparent motion changes in measurable ways. Curvature on the sky becomes clearer. The rate of change of the motion vector can be measured. This provides stronger constraint on the heliocentric distance and on the orbital energy. Orbital energy is what distinguishes bound from unbound motion. In a gravitational two-body approximation, the object's energy relative to the Sun determines whether it is on an ellipse parabola or hyperbola. With a longer arc, the energy estimate becomes more stable because the observed motion captures more of the gravitational influence of the Sun. The difference between a very long period bound orbit and a slightly unbound orbit becomes easier to distinguish when the object is observed over a range of heliocentric distances. Even if the object remains far from the Sun, the changing geometry as Earth moves can provide additional parallax leverage over weeks. The orbital inclination and orientation also become more stable because the track covers a larger portion of the sky. One key practical element in extending the arc is the handoff from survey detection to targeted follow-up. Surveys are optimized for scanning large areas quickly. Their exposures are often short. Their resolution may be moderate. Follow-up telescopes can stare longer at the object, collecting more photons and producing higher signal-to-noise detections. They can also track at the object's apparent rate, keeping it point-like while stars trail. That can improve photometry and, in some cases, astrometry, though it complicates star-based calibration. Some follow-up campaigns use multiple telescopes with complementary capabilities. A smaller telescope may provide frequent position updates. A larger telescope may provide deep images that reveal faint coma or faint fragments. A telescope at a different longitude can observe when local night differs, filling gaps and reducing the time between measurements. This distributed approach reduces the risk of losing the object. As parameters tighten, analysts update the ephemeris, the predicted positions, for future times. The ephemeris includes not only the nominal position, but also an uncertainty. Observers use this to schedule. They also compute rates of motion and expected brightness. Rate of motion matters for exposure choice. If the object moves quickly, long exposures will trail it unless tracking is adjusted. Expected brightness matters for choosing exposure duration and telescope size. Brightness predictions are uncertain early on because they depend on the object's intrinsic brightness and on how it responds to changing distance from the Sun and Earth. For a cometary object, brightness can increase rapidly as it approaches the Sun due to outgassing and dust production. For an asteroid, brightness changes mostly with distance and viewing angle. In the arc extension stage, repeated photometric measurements begin to show which pattern applies, though mixed behavior is possible. Tightening orbital parameters also reveals whether the object's motion is consistent with purely gravitational dynamics. Residuals are monitored over time. If residuals remain random and within expected uncertainties, a gravitational model may be adequate. If residuals begin to show systematic deviation, such as a consistent offset that grows with time, then either the model is missing a force or the measurements have a systematic bias. At this stage, the first suspicion often falls on measurement issues. Perhaps the coma is shifting the centroid. Perhaps different observatories have small frame biases. Perhaps timing issues exist. Analysts test these possibilities by segregating data by observatory, by measuring whether residual patterns correlate with observing conditions, and by comparing astrometry methods. If the systematic deviation persists across independent datasets, then attention turns toward physical explanations, such as non-gravitational acceleration from outgassing. But even then, the arc extension phase is where the evidence must be built. A claim that the object's path is changing must be backed by a stable gravitational fit that fails in a consistent way. One sign of a genuinely improving orbit is that the covariance shrinks. The uncertainty ellipsoid in parameter space becomes smaller. The line of variation on the sky becomes shorter. Predicted positions become more precise. Recovery becomes easier because the search region shrinks. This positive feedback accelerates the campaign. More telescopes can be scheduled because the target position is reliable. More data can be gathered because the object is not lost. This is how small bodies become well characterized. The arc extension phase also includes the possibility of linking the object to earlier unnoticed detections. Once the orbit is better constrained, analysts can search archival survey images more effectively because the predicted past positions have smaller uncertainties. A successful precovery extends the arc dramatically and tightens the orbit further. Even a single precovery point months earlier can transform the solution. If no precovery is found, that absence can still constrain the orbit because it suggests the object was too faint or in a different sky region than certain candidate paths would predict. In this way, the growing arc is not just a tally of points, but a progressive narrowing of the object's plausible history and future. In the case of 3I Atlas, this phase is where the object becomes predictable enough for deeper physical questions to be asked. The work remains observational in spirit, grounded in repeated position measurements and careful statistical treatment, but it moves inward by making the orbit a stable scaffold. Only on such a scaffold can deviations, if they exist, be identified as real. The tightening of parameters is therefore a disciplined transition from provisional trajectories to a reliable path achieved through coordinated observation, careful calibration, and continuous testing of predictions against new data. With the trajectory becoming more stable, the analysis can move one step inward from motion and orbit geometry to the physical bounds implied by brightness distance and reflected sunlight. This step remains cautious because a small body's brightness is not a direct measure of size. It is an observable that blends distant surface reflectivity and, in some cases, additional light from dust and gas. Still brightness provides constraints, and those constraints are essential when judging whether an object behaves in a way that seems inconsistent with expectations. The starting point is apparent brightness, the measured light reaching the telescope. Apparent brightness changes as the object's distance from Earth changes and as its distance from the Sun changes. The Sun provides the light that an inert object reflects. If the object is closer to the Sun, it receives more sunlight and can reflect more. If it is closer to Earth, its reflected light spreads over a smaller sphere before reaching the observer, making it appear brighter. There is also a geometric factor called phase angle, the angle between the Sun, the object, and Earth. When the phase angle is small, Earth sees more of the sunlit side, and the object can appear brighter. When the phase angle is large, Earth sees a thinner crescent of illumination, and the object appears dimmer. For rough surfaces, brightness can increase sharply at very small phase angles due to a phenomenon known as the opposition surge, caused by shadow hiding and coherent backscatter. These effects matter most for solid bodies, and they remind the observer that brightness is shaped by geometry as well as physical size. To relate brightness to size, analysts use the concept of absolute magnitude, a standardized brightness the object would have if it were at a defined distance from both the Sun and Earth and viewed at a standard phase angle. Absolute magnitude is useful because it removes the main distance effects. For asteroids, a relation exists between absolute magnitude, albedo, and diameter. Albedo is reflectivity, the fraction of sunlight reflected. A dark object with low albedo must be larger to reflect the same amount of light as a bright object with high albedo. Without knowing, albedo diameter remains uncertain. Many small bodies have albedos spanning a wide range. Some are dark with albedos of only a few %. Others are brighter with higher albedos. Therefore, an absolute magnitude translates into a range of possible diameters. The uncertainty can be a factor of several. For an object like 3I Atlas, albedo is not known at first, so size estimates must be expressed as bounds. Analysts may adopt a typical dark comet like albedo to produce an upper size bound and a more reflective asteroid like albedo to produce a lower size bound. This provides a bracket rather than a single number. The bracket becomes tighter only if additional observations constrain albedo, such as thermal infrared measurements that detect heat emission. Thermal emission depends on size and surface properties in a different way than reflected light. If both reflected light and thermal emission are measured, size and albedo can be solved more directly. Without thermal data, reflected light alone cannot uniquely determine size. Brightness can be further complicated if the object is not a bare, solid body. If it releases gas and dust, the surrounding coma can contribute to the observed light. Dust grains scatter sunlight efficiently, and a small amount of dust can create a large, bright cross-section. In that case, the observed brightness may not come primarily from the nucleus, the solid core. It may come from the dust cloud. This can make the object appear much larger than the nucleus. A comet can therefore look bright and diffuse, even if the nucleus is modest in size. If 3I Atlas shows any sign of extended appearance, such as a fuzzy halo or an asymmetry suggesting a tail, then the brightness must be interpreted with caution. Analysts use image profile measurements to assess this. They compare the object's point spread function to that of nearby stars. If the object's profile is broader than stars, it may be extended. They also look for changes in profile with time or with filter, because gas emission lines can brighten the object in specific filters while dust dominates others. If the object remains point, like that suggests little to no coma at the level detectable. However, even a point-like image does not guarantee no activity, because a small coma can be unresolved if the seeing is poor or if the object is far away. Another complication is rotation. If the object rotates and has an irregular shape, the projected area can change with time, producing periodic brightness variations called a light curve. A rotating, elongated body can brighten and fade as different cross-sections face Earth. The amplitude of this variation can provide clues about shape and rotation period. For example, large amplitude variations suggest a very elongated shape or strong albedo variations across the surface. Small amplitude variations suggest a more spherical shape or a pole oriented toward Earth. For a faint object, measuring a light curve requires repeated high signal-to-noise observations over hours or days. If measured, the light curve can help separate nucleus brightness from coma brightness. A coma tends to smooth out rotational variations because it adds a steady contribution. Therefore, a strong periodic light curve can suggest a bare or lightly active nucleus. A weak or absent light curve can suggest either a near spherical body, a rotation axis aligned with Earth, or the presence of coma-diluting variations. Distance estimates from orbit determination also feed back into brightness interpretation. Once the orbit is better constrained, the heliocentric and geocentric distances at each observation time are known with more confidence. Analysts can then correct the observed brightness for the changing distances and phase angle to compute an evolving absolute magnitude. If the corrected brightness remains roughly constant, that suggests the object's intrinsic brightness is stable, consistent with a non-active body. If the corrected brightness increases as the object approaches the Sun beyond what geometry predicts, that suggests activity such as sublimation of ices producing dust. Activity onset often occurs when the object reaches certain temperatures, which depend on distance from the Sun and on surface properties. Water-ice sublimation becomes significant closer to the Sun, while more volatile ices like carbon dioxide or carbon monoxide can sublimate farther out. Therefore, a distant comet can show activity if it contains more volatile material, or if its surface allows heat to reach volatile layers. If 3I Atlas appears to brighten unexpectedly at large distance, that would be consistent with such volatiles, but it would still require careful separation of measurement bias from real change. Measurement bias can arise from changing background from different telescopes with different filters and calibration, or from the object moving into a more crowded field. A consistent brightness increase across multiple instruments and conditions would be more convincing than an increase seen in one dataset. Analysts also consider the slope of the brightness change with distance. For a purely reflective body, brightness approximately follows an inverse fourth power law with respect to distance, when both Sun object and Earth object distances change, though the exact dependence varies with geometry. For an active comet, brightness can follow steeper laws because dust production increases rapidly as sunlight increases. Measuring this slope helps characterize the object. Still, the slope can vary with time and can show outbursts, sudden increases in activity. Outbursts can be caused by fresh ice exposure, pressure buildup, or fragmentation events. In brightness data, an outburst appears as a jump. if 3i Atlas shows such jumps that might later be confused with a response to external triggers. But brightness-driven physics can produce abrupt changes without any external signal beyond increasing solar heating and internal structure. In this section, the essential point is that brightness and size are linked, but not identical. The observed light sets bounds on the object's reflective cross-section, but translating that into nucleus size requires assumptions about albedo and activity. The work therefore proceeds by building conservative brackets and by searching for independent constraints, such as infrared emission-resolved coma or consistent light curve behavior. As the object's physical bounds are better understood, later claims about unusual acceleration or responsiveness can be tested against plausible mass and surface activity levels. For now, the inward step is to treat the object not only as a trajectory, but as a body with a limited range of possible sizes and surface behaviors inferred from the careful interpretation of its brightness against the known geometry of its distances and illumination. With brightness-based bounds in place, the analysis moves inward from simple reflected light to the direct observational signs of activity, the ways a small body can reveal material loss into space. In practice, activity is diagnosed through appearance and through changes that cannot be explained by a bare rotating solid alone. For comets, the classic indicators are a coma and a tail. A coma is a cloud of gas and dust surrounding the nucleus produced when sunlight warms surface or near-surface ice, and volatile compounds change from solid to gas, a process called sublimation. The expanding gas drags dust grains away from the surface. The coma can be roughly spherical near the nucleus, then shaped by solar radiation pressure, and the solar wind into tails that point away from the sun or along the object's path. For an object like 3i Atlas, the first question is whether the image is point-like or extended. This is tested by comparing the object's profile to nearby stars observed in the same exposure. Stars provide a reference for the atmospheric and optical blur. If the object is broader than stars, that suggests extended emission. Even a subtle broadening can be meaningful if it is consistent across multiple exposures and instruments. Analysts can quantify this by measuring the full width at half maximum of the brightness profile, a measure of how wide the central light distribution is. If the object consistently has a larger width than stars, and if the difference cannot be explained by trailing or focus changes, then a coma is likely present. However, the width test is sensitive to seeing conditions. Turbulence can vary across an image and across exposures. Therefore, the comparison must use stars close to the object in the same frame, not stars far away or from different nights. A second method is image stacking. If multiple exposures are taken, they can be shifted to a line on the object and added together. This increases signal-to-noise and can reveal faint, extended structures. When stacking on the object, stars trail, but their trails can be masked or modeled. A stacked image can show a faint halo or a short tail that is invisible in single frames. The direction of any tail relative to the sun and to the object's motion is then examined. A dust tail tends to align roughly away from the sun, though the exact direction depends on dust grain sizes and the object's velocity. An ion tail composed of gas molecules pushed by the solar wind points more directly away from the sun and can be narrow. At large distances, activity can be weak, and tails can be short or absent even if gas is present. Therefore, the absence of a visible tail does not necessarily mean no activity. Photometry provides another diagnostic. If the object's brightness increases more rapidly than expected from distance changes alone, that suggests an expanding scattering cross-section, often due to dust release. Analysts correct the observed brightness for changing distances to compute an intrinsic brightness trend. They look for systematic brightening beyond what a stable nucleus could produce. They also look for color changes. Dust scattering has a certain color dependence, often appearing slightly redder than sunlight, because larger grains scatter longer wavelengths more efficiently. Gas emission can produce different colors if certain emission lines fall within a filter's bandpass. By measuring brightness in multiple filters, analysts can detect whether the object's spectrum is consistent with reflected sunlight or whether it includes additional emission. A spectrum, if obtainable, is a stronger tool. Spectroscopy spreads the object's light into wavelengths and can reveal emission features from common comet gases, as well as the continuum from dust. At the distances where 3I Atlas is detected, obtaining a spectrum may require large telescopes, but even low-resolution spectra can separate pure reflection from gas emission. Still, spectra of faint objects carry noise and must be interpreted carefully. A weak feature can be mistaken for noise or for imperfect subtraction of sky emission lines from Earth's atmosphere. Therefore, repeated spectra and consistent detections are needed before strong claims are made. Another sign of activity is asymmetry in the coma. A perfectly symmetric coma centered on the nucleus suggests steady isotropic outgassing. Many comets, however, show jets localized streams of gas and dust from active areas on the nucleus. Jets can create a fan-shaped structure or a bright knot offset from the nucleus. As the nucleus rotates, jets can turn in and out of sunlight, changing strength and direction. This can cause the coma to change appearance over hours and days. Such changes can look like a pattern, and in casual language they might be described as the object reacting. In physical terms, they are a consequence of rotation surface heterogeneity and the changing angle of sunlight. The geometry of the Sun relative to the nucleus changes as the object moves along its orbit. Even at a fixed distance, the orientation of the rotation axis relative to the Sun can change the distribution of heating across the surface, altering activity. Therefore, the appearance of turning on and off can occur naturally as different areas receive sunlight. The onset distance for activity is also informative. Water ice sublimation becomes strong at relatively small heliocentric distances. Farther out, water ice is cold and sublimation is weak. Yet comets can still be active far from the Sun due to more volatile ices such as carbon monoxide or carbon dioxide, or due to the release of trapped gases. Some bodies also show dust emission driven by thermal fracture or by crystallization of amorphous water ice. Amorphous ice is a disordered form that can trap volatile gases. When it warms and transforms to a crystalline state, it can release trapped gases and drive outgassing even at relatively low temperatures. This process can produce activity at distances where water ice sublimation alone would not. Another driver is the sublimation of supervolatiles, which can occur at tens of astronomical units depending on composition. Therefore, activity does not automatically mean the object is close to the sun. It means that some mechanism is producing gas flow. For a body coming from interstellar space, composition might differ from typical solar system comets. But even within the solar system, comets show a wide range of activity patterns. The presence of activity also affects astrometry and orbit determination. A coma can shift the measured centroid away from the nucleus if the brightness distribution is asymmetric. This can introduce systematic errors in measured positions. If analysts are not careful, such centroid shifts can appear as trajectory deviations. Therefore, when activity is suspected, orbit fitters may use specialized astrometry methods that attempt to locate the nucleus within the coma, or they may assign larger uncertainties to positions. They may also examine whether residuals correlate with changes in brightness or coma morphology. A correlation would suggest that apparent motion anomalies are linked to measurement effects rather than true forces. Another activity sign is fragmentation. A nucleus can split into multiple pieces, producing multiple points of light or a complex structure. Fragmentation can be gentle, producing a faint companion, or violent, producing a cloud of debris. In images, fragments can appear as separate condensations within the coma. Over time, fragments drift apart due to small relative velocities. Fragmentation can produce sudden brightening because it exposes fresh ice and increases the total surface area that sublimates. It can also change the dust environment, producing new tails or broadened coma. If 3I Atlas were to show evidence of fragments, that would be a major physical development that could later be confused with a purposeful change. In physical terms, it is a structural failure driven by thermal stress, internal pressure, or weak cohesion. The energy source remains sunlight and internal dynamics, not external signaling. In this section, the analysis stays close to observation. The question is what the images and brightness data reveal about material loss. Activity is not inferred from narrative language. It is inferred from extended profiles, asymmetries, brightness trends beyond geometric expectations, spectral features, and in some cases, fragmentation signatures. Each diagnostic has limitations, and each must be confirmed across independent observations. Yet together, they form a coherent set of tests. If activity is present, the object becomes not just a reflecting body, but a source of gas and dust. That changes the physical forces acting on it and sets the stage for the next inward step, where small non-gravitational accelerations can be measured and attributed to outgassing. For now, the focus remains on establishing whether 3I Atlas shows the observational fingerprints of activity, and on doing so in a way that does not confuse measurement artifacts with real physical emission. With observational signs of activity established as a possibility, the analysis moves inward to the level where forces are inferred from deviations in motion, the domain of non-gravitational acceleration. In orbit fitting, the default assumption is that gravity dominates with the Sun as the primary source and the planets providing perturbations. When an object is inert, this assumption is usually adequate. When an object releases gas and dust, it can experience small thrusts. Gas molecules leaving the surface carry momentum. By conservation of momentum, the nucleus experiences a reaction force in the opposite direction. This is similar in principle to a rocket, though the thrust is typically tiny and irregular compared to engineered propulsion. Over short times, the effect may be negligible. Over weeks and months, tiny accelerations can accumulate into measurable trajectory shifts. Detecting such accelerations requires a stable gravitational solution and high-quality astrometry. The logic is ordered. First, a gravitational model is fit. Then, residuals are examined. If residuals show systematic trends that cannot be eliminated by improving astrometry or adjusting planetary perturbations, then an additional acceleration term is considered. The simplest non-gravitational model treats the acceleration as a function of distance from the Sun, because sunlight drives sublimation. As the object approaches the Sun, heating increases and gas production increases, raising thrust. As it recedes, thrust decreases. A widely used approach defines an empirical function that approximates water-ice sublimation and scales acceleration components along three orthogonal directions, tied to the orbit: one radial direction, away from the Sun; one transverse direction, along the direction of motion; and one normal direction, perpendicular to the orbital plane. Coefficients for these components are fit to the data. The fitted coefficients quantify how strong the non-gravitational acceleration is and in what directions it acts on average. Even this simple model carries assumptions. It assumes a certain symmetry and a certain relationship between heating and outgassing. Real comets can deviate because active areas are localized, because the nucleus rotates, and because thermal lag can delay outgassing relative to peak sunlight. Thermal lag occurs when heat takes time to conduct into the surface and subsurface layers where volatiles reside. In such cases, the maximum gas production may occur after the maximum solar heating, producing an acceleration that is not perfectly symmetric around perihelion, the closest approach to the Sun. Therefore, more sophisticated models allow a time shift. Still, the first goal is to detect whether any consistent non-gravitational term is required at all. The detection threshold depends on measurement quality. If astrometric uncertainties are larger than the expected displacement from non-gravitational acceleration over the observed arc, then the acceleration cannot be reliably detected. If the object is bright and point-like astrometry can be precise enough to detect very small accelerations. If the object is faint or has an extended coma, the centroid uncertainty can mask acceleration. Therefore, an object that is strongly active can sometimes be harder to analyze in this way, because the measurement of the nucleus position becomes less certain. Analysts address this by selecting astrometry that is less affected by coma, or by using techniques that model the coma and identify the central condensation corresponding to the nucleus. They also compare results across different observatories to avoid relying on a single systematic bias. When a non-gravitational acceleration is detected, its magnitude can be translated into constraints on mass loss. The thrust depends on the rate of gas emission and the speed of the gas. Gas speeds depend on temperature and on molecular mass. At typical comet temperatures near the inner solar system, gas speeds can be hundreds of meters per second to around a kilometer per second. Farther out, gas speeds can be lower. The thrust is the product of mass loss rate and gas speed adjusted by the directionality of the emission. If gas flows uniformly in all directions, thrust cancels out and net acceleration is small. Net acceleration requires asymmetry, such as jets on one side. The object's mass then determines how much acceleration results from a given thrust. A small, low-mass nucleus can be pushed more easily than a large, massive one. This is why size bounds from brightness matter. If an object seems to experience a strong acceleration but also seems large, the implied mass loss rate might be very high, potentially inconsistent with observed activity. Conversely, a smaller nucleus could experience the same acceleration with a more modest mass loss rate. Analysts therefore cross-check. They compare the required thrust to the observed brightness of the coma and tail, which reflects dust production, and to any detected gas emission. If the required mass loss is far larger than what is consistent with observations, then either the acceleration is not real, the size estimate is wrong, or the object's properties are unusual in a way that changes the relation between observed brightness and mass loss. Another key point is direction. A purely radial acceleration away from the sun is a common signature of outgassing because sunlight-driven sublimation tends to be strongest on the sunlit side. However, the net thrust direction can differ depending on nucleus rotation and jet location. Transverse acceleration can change the orbital period or energy more directly. Normal acceleration can tilt the orbit. Therefore, the pattern of acceleration components can provide clues to the geometry of outgassing. Yet these clues are probabilistic rather than definitive, because many jet configurations can produce similar average components. The apparent idea that an object is responding to something often arises when the acceleration seems to change over time. In data terms, this can mean residuals that are not well fit by a simple symmetric model. Several physical mechanisms can produce time-variable acceleration without any external trigger beyond sunlight. One is rotation modulation. If an active region turns in and out of sunlight, thrust can vary on the rotation period. If the rotation period is hours, the acceleration variations may average out over days, but they can still affect astrometric residuals if observations sample certain rotation phases more than others. Another is seasonal change on the nucleus. As the object moves the subsolar point, the point receiving direct sunlight shifts across the surface, depending on the tilt of the rotation axis. This can activate new regions and deactivate others, changing thrust direction and magnitude over weeks. Another mechanism is fragmentation or surface collapse. If a piece breaks off and exposes fresh volatile material, gas production can increase, suddenly producing a change in acceleration. This can look like a sudden change in trajectory if measured. It is a physical change in the body driven by internal structure and heating. Another mechanism is depletion. If an active patch exhausts its accessible volatiles and becomes insulated by dust activity, can decline even as the object approaches the sun. This can produce a weakening acceleration where a simple model would predict strengthening. Thermal lag can also produce a phase shift. The peak thrust may occur after peak heating, and the shift can depend on thermal conductivity and layering. Therefore, the acceleration can appear to respond with a delay. These are all normal physical behaviors for small bodies with volatile materials. A related issue is that non-gravitational acceleration is sometimes inferred incorrectly when the gravitational model is incomplete or when measurement errors are not properly handled. For example, if star catalog systematics introduce a small bias in measured positions that changes as the object moves across the sky, residuals can mimic acceleration. If coma-induced centroid shifts grow as activity increases, residuals can mimic acceleration that correlates with brightness. Analysts test this by comparing residuals to observing geometry and to brightness. They may also compute solutions using only high-quality subsets and see whether the acceleration term persists. They examine whether the inferred acceleration is consistent across independent astrometry sources. A real physical acceleration should be supported by multiple independent datasets. If it appears only when certain measurements are included, it may be an artifact. When the acceleration is robust, it becomes a quantitative measure. It can be expressed in units of acceleration and compared to gravitational acceleration from the Sun at the object's distance. Solar gravitational acceleration decreases with the square of distance. Non-gravitational acceleration from outgassing can be many orders of magnitude smaller than solar gravity, yet still measurable. The comparison helps keep scale. Even a small fraction can shift an orbit over time. The key is accumulation. Over a month, a tiny constant acceleration can change velocity by a measurable amount. Over months, it can change the predicted sky position by arcseconds or more, enough to matter for recovery and for claims of unusual behavior. In this section, the analysis therefore becomes an exercise in careful attribution. Deviations from gravitational motion are measured. Models for sunlight-driven outgassing are fitted. The required thrust is compared to observed activity and size bounds. Time variability is considered in the context of rotation, seasonal illumination, thermal lag, and fragmentation. The language of response is replaced by the language of forces and residuals. If 3I Atlas shows an acceleration that cannot be explained by gravitational dynamics alone, that does not automatically imply anything beyond known comet physics. It implies that the object is exchanging momentum with escaping material. The shape and evolution of that exchange can be complex, and it can produce patterns that appear purposeful when described casually. The task here is to establish the magnitude and structure of any non-gravitational acceleration in a way that is consistent with the data and with the physical mechanisms that are already known to operate in small bodies exposed to sunlight. Once non-gravitational acceleration is identified as a possibility, the analysis moves inward to the mechanisms that can create changing thrust patterns with rotation and jet behavior as the primary drivers. A small body is rarely uniform. Its surface can include regions of different composition, different dust cover thickness, and different exposure to sunlight. If volatile materials exist beneath a dusty crust, they may only vent where cracks, pits, or thin spots allow heat to reach them. When gas escapes through such openings, it can entrain dust and form jets. A jet is not a steady engine. It is a flow governed by illumination, local temperature, and the geometry of vents and shadows. The nucleus also rotates often with a period of hours to days. Rotation changes which regions face the sun and which face away. This creates a natural cycle of activity that can appear to switch on and off. In observational data, this can show up as periodic brightness changes, as changes in coma shape, and as changes in the direction and magnitude of non-gravitational acceleration. The first step is to understand how rotation is measured. For a mostly inert body, rotation is often inferred from a light curve, periodic changes in brightness, caused by changing projected area as the body spins. For an active body, the light curve can be complicated because the coma adds a smoothing component, and because jets can brighten the object in a way that is not purely geometric. Still, periodic patterns can be detected if enough high-quality photometry is gathered. A repeating cycle of brightening and fading suggests a rotation period, or a multiple of it. In some comets, jets create repeating features that move around the nucleus as it rotates. Observers can sometimes track the position angle of a jet over time, which provides a direct clue to rotation and pole orientation. The rotation axis orientation, often called the spin pole, matters because it sets the seasonal pattern of sunlight on the surface. If the pole is tilted relative to the orbit plane, then as the object moves along its orbit, the sun shines on different latitudes. A region that is in constant daylight for part of the orbit can become shaded later and vice versa. This can produce long-term changes in which vents are active. The physics of jet formation begins with heat. Sunlight warms the surface. Heat conducts downward, and when it reaches volatile material, sublimation begins. Gas builds pressure in pore spaces and fractures. If the overlying material is permeable, gas can percolate through and escape diffusely. If there is a constricted path, gas can escape as a collimated jet. The gas flow can carry dust grains. Dust grains range from tiny micrometer-sized particles to larger grains and pebbles. Smaller grains are more easily lifted. Larger grains require stronger gas flow. Once lofted dust grains are influenced by the sun's radiation pressure, a force from sunlight itself. Radiation pressure pushes grains away from the sun, and its effect depends on grain size. Small grains are pushed strongly relative to their mass. Large grains are pushed less. The combination of initial gas flow and subsequent radiation pressure shapes the dust tail. Near the nucleus, the jet may point in a direction set by the vent geometry. Farther out, the dust is redirected away from the sun. Therefore, the apparent direction of a jet in images can change with distance from the nucleus and with time. If the nucleus rotates, the jet source moves in the object's frame, sweeping a cone through space. The resulting dust distribution can create a spiral or fan structure in the coma. These patterns can be visible in high-resolution images and can evolve predictably with rotation. Even without visible patterns, rotation can modulate the total dust production. When an active region faces the sun, it warms and produces gas. When it rotates into darkness, it cools and production decreases. This on-off cycle can be softened by thermal inertia, the tendency of the material to retain heat. If the active layer is beneath the surface, it may continue sublimating after the surface rotates into darkness because stored heat continues to flow downward. This creates a lag. The lag can shift the peak activity away from the moment of maximum sunlight. The lag depends on thermal conductivity depth of the volatile layer and the thickness and properties of the dust mantle. A thick insulating mantle can delay heating and reduce peak sublimation. A thin mantle can allow more rapid response. Therefore, rotation-driven modulation can produce patterns that look like responsiveness with delay. In terms of forces, the thrust from outgassing is the vector sum of momentum carried away by gas and entrained dust. The direction of the net thrust depends on the location of active vents and on the direction of the gas flow. If the primary active area is near the sub-solar point, the net thrust tends to be roughly away from the sun. If the active area is offset, the thrust can have a transverse component. As the nucleus rotates, the thrust direction can vary over a rotation period. However, the orbit determination process typically fits accelerations over longer timescales, so short-period variations may average out. They can still matter if observations are not uniformly distributed. For example, if most astrometric observations are taken at similar local times each night, and if the rotation period is close to a day or a fraction of a day, observations may sample similar rotation phases repeatedly. This can imprint a bias. It can make the average thrust appear stable or unstable depending on sampling. Analysts are aware of this and seek observations at different times to break aliasing the confusion of one period with another. Rotation can also change over time. Outgassing itself can apply torque, a twisting force that changes spin rate and spin axis. This is observed in some comets. As jets vent, they push not only the center of mass, but also produce a lever arm if the vent is off-center. Over time, this can speed up or slow down rotation. It can also cause precession, a slow wobble of the rotation axis. Changes in rotation can alter jet patterns and activity cycles. In extreme cases, rapid spin-up can lead to structural failure and fragmentation because the centrifugal force can exceed the weak cohesion of the nucleus. Therefore, rotation is both a driver of activity and a variable that can evolve due to activity. This feedback can produce complex behavior without any external control. The apparent idea that an object is reacting to something can arise when observers see changes that correlate with time, with distance, or with viewing geometry. For example, a jet might become visible at certain viewing angles and disappear at others. This can be a pure projection effect. If the jet points toward Earth, it may be harder to see as a separate structure. If it points sideways, it may be more obvious. Similarly, a dust tail may appear longer when the phase angle is favorable. Therefore, morphological changes must be interpreted in 3 dimensions, not as intrinsic switching alone. Observers use the known positions of the Sun and Earth relative to the object to model expected tail directions and to interpret features. Another point is that jets can be episodic. Gas flow through a vent can be choked by collapsing dust, then reopen. A vent can be sealed by frost deposition during darkness and then reopen when warmed. Pressure can build beneath a crust and release suddenly. These processes can create bursts of activity, producing sudden brightening and transient jets. Such bursts can be triggered by internal conditions reaching a threshold which is controlled by heating and material properties. They can look sudden from the outside, but they arise from gradual buildup. In a data set, such bursts can coincide with certain distances or times, and casual interpretation may treat them as responses to external events. In physical terms, they are responses to sunlight mediated by the object's structure. In this section, the analysis remains within the scope of known small-body physics. Rotation provides a clock. Jets provide directionality. Thermal inertia provides lag. Outgassing torques provide evolution. Together, they can produce time-variable acceleration and changing appearance. If 3I Atlas shows behavior that seems patterned, the first inward explanation is that the nucleus is rotating and that active areas respond to sunlight with delays and thresholds. This does not claim that such explanations must be correct. It establishes a physical basis for complexity that does not require novel forces. The next inward steps will examine how heating near the sun sets the overall thermal context and how fragmentation and dust dynamics can amplify changes. But here, the focus is the moving surface itself. Turning in sunlight, venting where it can, and shaping the observed behavior through the interplay of rotation jets and thermal properties. From rotation and jet behavior, the analysis moves inward to the thermal physics that sets the conditions for sublimation crust formation and delayed or nonlinear responses as the object moves through different sunlight levels. Thermal physics here is not abstract. It is a set of constraints on how quickly heat flows, how deeply it penetrates, and which materials can change phase at given temperatures. The surface of a small body in space experiences a balance between absorbed sunlight, emitted infrared radiation, and heat conducted into the interior. The absorbed sunlight depends on distance from the sun and on albedo. A darker surface absorbs more. A brighter surface reflects more. The emitted infrared radiation depends on surface temperature and on emissivity, a measure of how efficiently the surface radiates heat. Most rocky and dusty surfaces have emissivities close to 1, meaning they radiate efficiently. The conducted heat depends on thermal conductivity and on the structure of the near-surface layer. Many small bodies have porous regolith, a layer of loose grains. Porosity lowers thermal conductivity because heat must pass through grain contacts and through vacuum gaps. As a result, heat penetration is often shallow on diurnal timescales. The surface can heat and cool rapidly, while deeper layers change slowly. This creates a thermal wave that penetrates to a depth that depends on thermal diffusivity and on the period of heating. For a rotation period of hours, the diurnal thermal wave may reach only centimeters to decimeters. For seasonal timescales along the orbit, the thermal wave can reach deeper, perhaps meters, depending on material properties. Volatile ices can reside beneath a dust mantle. If the dust mantle is thick enough and insulating enough, the volatile layer can remain cold and inactive until the object approaches closer to the sun or until heat accumulates over time. This can create delayed onset. Activity can begin suddenly when the temperature at the volatile layer crosses a threshold where sublimation becomes significant. The threshold is not a single sharp value because sublimation rate increases gradually with temperature, but the increase can be steep. A small change in temperature can produce a large change in vapor pressure. This steep dependence can make activity appear to turn on. If the object's distance from the sun decreases slowly, the subsurface temperature may still rise and eventually reach a regime where gas production accelerates quickly. If gas escapes through pores, it can lift dust and create a coma. If gas is trapped beneath a less permeable crust, pressure can build. When pressure exceeds the strength of the crust, it can fracture, producing a burst of gas and dust. This burst can appear as an outburst, a sudden brightening. The energy source is still sunlight, but the response is nonlinear because the system includes thresholds and mechanical failure. Another thermal process is the development of a dust mantle. As ice sublimates, non-volatile dust and rock grains can be left behind. Over time, these grains can accumulate on the surface, forming an insulating layer. This mantle can reduce sublimation by limiting heat flow to the ice. It can also reduce gas escape by clogging pores. This can cause activity to decline even as sunlight increases because the mantle thickens. The mantle can also shift where activity occurs. If a region builds a thick mantle, it may become inactive. Another region with thinner cover may remain active. Therefore, activity patterns can migrate. In addition, mantles can be unstable. If gas pressure builds beneath a mantle, it can lift and collapse it. If a mantle collapses, it can expose fresh ice and restart activity. These cycles can create intermittent behavior. Thermal lag plays a central role in interpreting timing. The surface receives maximum sunlight at local noon. If the active ice is beneath the surface, the maximum temperature at that depth can occur later because heat takes time to diffuse downward. This creates a phase lag between illumination and gas production. On the scale of the orbit, the maximum heating occurs near perihelion, but the maximum outgassing can occur after perihelion if the subsurface continues warming. Many comets show such asymmetry. Therefore, an acceleration pattern that peaks after perihelion can be consistent with thermal physics. Conversely, if activity peaks before perihelion, it could reflect different layering or volatile composition. Volatile composition is another inward layer. Different ices have different sublimation temperatures. Water ice becomes important at relatively warm temperatures, and thus closer to the sun. Carbon dioxide sublimates at lower temperatures, allowing activity farther out. Carbon monoxide sublimates at even lower temperatures and can drive activity at large distances. An object with abundant carbon monoxide could show activity when water ice would remain mostly inert. Moreover, even if water ice is present, it can be sealed beneath a mantle and remain inactive until closer. Meanwhile, small amounts of more volatile ices can drive weak activity at larger distances. If 3I Atlas shows activity at distances where water-driven sublimation is unlikely, that would not require new physics. It would suggest the presence of more volatile materials or trapped gases released by other processes. One such process is the crystallization of amorphous water ice. Amorphous ice can form at very low temperatures and can trap volatile gases within its structure. When warmed, it transitions to crystalline ice, releasing trapped gases. This can provide a gas source without requiring the ice itself to sublimate strongly. The crystallization releases heat as well, which can amplify the process locally. This combination can produce bursts. The onset temperature for crystallization is higher than the cold outer regions, but can be reached at moderate distances from the sun, depending on the material. Therefore, crystallization is a candidate mechanism for activity beyond water sublimation. Thermal stress is another mechanism. As the surface heats and cools, it expands and contracts. Repeated cycles can crack the surface. Cracks can expose fresh, volatile, rich layers. Cracking can also change permeability, opening pathways for gas. If the nucleus is an aggregate of weakly bound material, thermal cycles can cause small landslides and collapses. These mechanical changes can alter activity patterns and can lead to sudden brightening. Again, the response can appear abrupt, even if driven by gradual heating. The environment around the object also matters. As the object approaches the sun, the solar wind becomes more intense, and the radiation field strengthens. Dust grains are pushed more strongly. Gas molecules can be ionized by sunlight and by the solar wind, creating ions that are swept away. The visibility of an ion tail can therefore increase with proximity to the sun. This can create an observational sense of the object becoming more active, even if the gas production rate is only moderately changing, because the environment makes the products more visible. Conversely, at large distances, gas may be present but hard to detect. Therefore, observational detection thresholds can imprint an apparent onset. Analysts compare observations at different wavelengths to address this. For example, infrared can detect warm dust, while optical detects scattered light. In some cases, radio observations can detect certain molecules or their products. Each window reveals different aspects of the thermal and chemical state. Thermal physics also feeds into non-gravitational acceleration. The thrust depends on gas flow, which depends on temperature, which depends on thermal properties. If the thermal lag shifts gas production, the acceleration can lag. If a mantle forms, acceleration can decline. If a crack opens, acceleration can spike. If volatiles of different types dominate at different distances, acceleration can change character with distance. Therefore, a changing acceleration is expected for an active body. The key is to see whether the changes match plausible thermal processes and whether they correlate with measured brightness and morphology. If acceleration increases while brightness increases and coma extends, that is consistent with stronger outgassing. If acceleration changes but brightness does not, it could reflect directional changes in jets rather than overall mass loss changes, or it could reflect measurement systematics. Analysts test these possibilities by looking at the direction of residuals relative to the Sun and to the orbital motion, and by comparing with images. In this section, the inward step is to anchor the object's behavior in heat flow. A small body does not respond instantly and smoothly to sunlight. It responds through a layered medium with low conductivity thresholds for phase change evolving surface mantles and mechanical failure modes. These features can generate delayed onset asymmetry bursts and migrations of activity. They can make an object's behavior look surprising if one expects a simple, smooth scaling with distance. Yet they are consistent with known comet and small body behavior. For 3I Atlas, the relevant question becomes which thermal regime it occupies at its observed distances, what volatiles could plausibly drive any observed activity, and how the interplay of insulation and lag can shape both appearance and trajectory. This thermal layer provides the context needed before moving further inward to the dynamics of fragmentation and dust, where structural changes can amplify thermal effects into dramatic observational events. From thermal physics, the analysis moves inward to fragmentation and dust dynamics, where structural changes in the nucleus and the behavior of released material can produce large observational effects and can also influence motion through mass loss and changing surface area. Fragmentation is common among comets because their nuclei are weakly bound aggregates of ice and dust, often with low tensile strength. As a nucleus warms, internal gas pressure can rise, thermal stress can crack it, and rotation can impose centrifugal forces. Any of these can exceed the material's strength and cause pieces to separate. Fragmentation can be subtle or dramatic. A subtle fragmentation might release small pieces that rapidly turn into dust, adding brightness without clearly resolved fragments. A dramatic fragmentation can produce multiple condensations that are seen as separate objects. In either case, the total effective scattering area can increase sharply, making the object brighten. This can be mistaken for an external trigger. In physical terms, it is a change in the distribution of material. The first observational signature of fragmentation is often a sudden change in brightness that exceeds the expected trend. If the brightness increases rapidly over hours or days, analysts look for a corresponding change in morphology. They examine whether the central condensation splits or elongates. They use stacked images to enhance faint features. They look for a fan-shaped dust distribution or for multiple peaks in the brightness profile. They also monitor the object's brightness afterward. A fragmentation event can produce a fast rise and then a slower decay as dust disperses. The decay timescale depends on particle sizes and on the forces acting on them. Dust grains are subject to radiation pressure. The smaller the grain, the larger the acceleration from radiation pressure relative to gravity. Small grains are pushed away from the sun, quickly forming a tail. Larger grains remain closer and form a more compact coma. Therefore, the brightness evolution contains information about the grain size distribution. If the object brightens and then fades quickly, it suggests a large fraction of small grains that move away rapidly. If it stays bright longer, it suggests larger grains that linger near the nucleus. Dust dynamics also affect the measured position. If the coma becomes asymmetric, the centroid measured in astrometry can shift. For example, if a dust tail is brighter on one side, the center of light can move away from the nucleus. This can introduce apparent positional shifts that mimic changes in trajectory. Therefore, during fragmentation or strong dust production, astrometry must be treated carefully. Analysts may switch to measuring the position of the sharpest central condensation rather than the centroid of the whole coma. They may use high-resolution images from larger telescopes to locate the nucleus. They may assign larger uncertainties to astrometry during periods of strong asymmetry. In addition, fragmentation changes the physical body that experiences thrust. If the nucleus splits, each fragment has its own mass and its own activity. Smaller fragments can experience stronger non-gravitational accelerations because they have lower mass relative to their surface area. If a fragment becomes the dominant bright source, the measured motion may shift to that fragment, altering the inferred acceleration. This can create apparent changes in acceleration that are not changes in the original nucleus, but changes in which piece is being tracked. Therefore, careful identification of the tracked component is essential. Analysts check whether the brightness peak corresponds to the largest fragment or to a transient dust condensation. Dust production itself can be driven by several mechanisms. Besides sublimation lifting, dust fragmentation can liberate dust directly. Collisions among fragments can produce dust. Rotational shedding can fling material off the surface. Thermal fracture can chip off grains. Once dust is in space, its motion relative to the nucleus is influenced by initial ejection velocity, and then by forces. The initial ejection velocity depends on gas flow. For comets near the Sun, dust can be ejected at tens to hundreds of meters per second, with smaller grains faster. Farther out, velocities can be lower. Even small velocities can spread dust over large distances over time. Radiation pressure then bends trajectories away from the Sun. The combination produces the dust tail shape. The tail is not a simple line. It is a time-integrated record of dust emission, with different grain sizes forming different curves. Observers sometimes analyze tail morphology using models that assume dust is emitted at certain times and sizes. By fitting the observed tail, they can estimate when an outburst occurred and what grain sizes dominate. This can link brightness changes to physical events. Another inward aspect is the relationship between dust and gas. Gas emission can be hard to see in images, but it can still drive dust. If gas production increases, more dust can be lifted. If the surface becomes depleted of fine dust, gas may escape without lifting much dust, reducing visible brightness, even if gas flow remains. Conversely, a fragmentation event can supply abundant fine dust, creating a bright coma, even if gas production does not increase proportionally. Therefore, brightness is not always a direct measure of gas production. This matters for interpreting non-gravitational acceleration. Acceleration depends primarily on gas momentum, though dust can contribute. If brightness increases due to dust without a matching increase in gas acceleration, may not increase as much as brightness suggests. Conversely, if gas increases without much dust acceleration, may increase while brightness changes modestly. Therefore, analysts compare multiple diagnostics, including spectra for gas and dust photometric colors and tail morphology. Fragmentation also changes the nucleus surface area. If a nucleus breaks, new surfaces are exposed. Fresh ice can sublimate strongly. This can increase gas production and thrust. It can also accelerate the evolution of a dust mantle as sublimation leaves behind debris. The new surfaces may be less insulated and may show more volatile, rich material. Therefore, fragmentation can mark a transition to a more active state. In this way, a single structural event can change both appearance and motion. It can create a step change in brightness and a step change in non-gravitational acceleration. Such step changes, when seen in residuals, can appear like a trajectory alteration. In physical terms, they are consistent with a change in outgassing regime caused by exposure of fresh material or by the creation of smaller fragments with higher surface-to-mass ratios. Another pathway to fragmentation is tidal stress during close planetary encounters. If an object passes near a planet, differential gravity across its body can create stress. For comets passing very close to Jupiter or other planets, this can contribute to breakup. Though thermal and rotational stresses are more common drivers for many objects, even without a close encounter, gravitational perturbations can change the object's rotation state by altering its orbit and thus its illumination history. For 3I Atlas, the relevant times are when it approaches the Sun more closely and when it passes near any major planet. The analysis in this section remains within the current region by focusing on the object's own material behavior rather than jumping to future encounters. Another dynamic effect of dust is non-gravitational force from anisotropic mass loss. When dust is ejected, it carries momentum. If dust emission is directional, it can contribute to thrust. However, dust speeds are usually lower than gas speeds, so the momentum per unit mass can be lower, but the dust mass can be large. In some cases, dust momentum can be significant. Moreover, dust can affect the object's torque if ejection is localized. This can alter rotation, feeding back into jet behavior. The interplay becomes complex, yet it remains grounded in conservation laws and in the known forces of sunlight and gravity. The overall picture is that fragmentation and dust dynamics can amplify modest thermal changes into large observational signals. A small change in internal pressure can lead to a crack, which leads to a burst of dust, which leads to a sudden brightening and a change in coma shape, which can shift astrometry, which can appear as a trajectory deviation if not accounted for. Therefore, careful sequencing is required. Observers examine images and brightness for evidence of fragmentation. They adjust astrometry methods accordingly. Analysts fit non-gravitational acceleration with awareness of changing tracked components. They model dust to interpret brightness transients. Through this, the apparent drama of sudden changes is translated into a chain of physical processes. If the claim is that 3i Atlas is responding to something, this section clarifies that fragmentation and dust release can create behavior that looks like a sudden decision, even though it can arise from the gradual progression of heat and stress reaching a failure threshold. The next inward step will examine how composition can be probed through spectra, which can anchor these processes in specific materials. But here the focus is the mechanical and dynamical behavior of material leaving the nucleus and reshaping what is seen. From fragmentation and dust dynamics, the analysis moves inward to spectral and compositional clues, where the object's light is used not only to measure position and brightness, but to infer what materials are present and what processes are active. Spectroscopy is the main tool here. It disperses the light into wavelengths, revealing the continuum of reflected sunlight from dust and nucleus surfaces, and revealing emission features from gas molecules excited by sunlight. For a faint object like 3i Atlas, spectra can be challenging. The signal is weak, the sky background is strong, and Earth's atmosphere introduces absorption and emission features that must be removed. Even so, compositional constraints can be obtained when observations are careful and when multiple measurements are consistent. A basic spectral distinction is between a pure reflected sunlight spectrum and a spectrum with emission bands. A bare, rocky, or dusty surface reflects sunlight and tends to produce a spectrum that resembles the sun's modified by the object's color. Many small bodies appear slightly redder than the sun, meaning they reflect more light at longer wavelengths than at shorter ones. This reddening can come from complex organic rich materials, from space weathering, and from the size distribution of surface grains. A cometary dust coma also produces a reflected sunlight continuum, often with modest reddening. Gas, by contrast, can produce narrow or banded emission features at specific wavelengths corresponding to molecular transitions. Common comet gases include cyanogen diatomic carbon and other radicals produced when sunlight breaks apart parent molecules like water carbon dioxide and carbon monoxide. In the near-infrared, water and carbon-bearing species can be detected in some cases. In the ultraviolet, certain species are also detectable, though this often requires space-based instruments. The presence of gas emission features indicates active sublimation and photochemistry. The absence of strong gas features does not prove inactivity because gas can be present below detection thresholds or in wavelengths not observed. Another compositional clue comes from color indices, which are simplified measures of the spectrum using broadband filters. By comparing brightness in different filters, observers can estimate whether the object is neutral red or unusually blue. A blue color could indicate strong gas emission in a particular band, or a dominance of small dust grains scattering shorter wavelengths more efficiently. A very red color could indicate organic rich dust or certain surface materials. Color can also change over time if activity changes the relative contributions of dust and gas. If gas emission increases, certain bands may brighten, changing the color. If dust production increases, the continuum may dominate and the color may reflect dust properties. Therefore, monitoring color over time can reveal changes in composition or in the dust-to-gas ratio. Spectra can also constrain particle size indirectly. The slope of the continuum and the presence of certain absorption features can indicate whether grains are fine or coarse, and whether certain minerals are present. For many comets, specific mineral absorption features are weak in the optical, but thermal infrared spectra can reveal silicate features indicating the presence of small silicate grains. These observations can sometimes be obtained when the object is closer and brighter. If 3I Atlas is observed in the thermal infrared, the measured emission can constrain both size and dust composition. Even without detailed features, the temperature of dust inferred from infrared emission can indicate grain properties and distance. Gas observations also extend beyond optical spectroscopy. Radio observations can detect rotational transitions of molecules such as carbon monoxide or other species if the object produces enough gas. These detections can directly measure gas production rates and velocities. They can also reveal whether the gas is coming from the nucleus or from distributed sources in the coma, such as sublimating icy grains. A distributed source can occur when grains containing ice are ejected and then sublimate in the coma, releasing gas away from the nucleus. This changes the spatial distribution of gas and can affect thrust. If gas is produced far from the nucleus, its contribution to thrust on the nucleus may be reduced because the momentum exchange occurs after ejection. Therefore, the spatial origin of gas matters for interpreting non-gravitational acceleration. Spectroscopic observations can sometimes constrain this by measuring how emission brightness falls off with distance from the nucleus. A steep decline suggests nucleus-centered production. A flatter profile suggests distributed production. Another inward aspect is isotopic ratios, such as the ratio of deuterium to hydrogen in water or ratios of carbon and nitrogen isotopes in certain molecules. These ratios are difficult to measure and require strong signals, but when measured, they provide deep clues about formation environment. For interstellar objects, isotopic ratios could potentially differ from typical solar system values, though there is overlap and uncertainty. In most cases, such detailed isotopic measurements are not available for faint objects. Therefore, the practical compositional analysis relies more on the presence or absence of certain common species and on broad dust properties. Still, even that can distinguish between an asteroid-like body and a comet-like body. A key question is whether the object shows the typical suite of cometary radicals in the optical. If cyanogen and diatomic carbon are detected, that suggests cometary activity. If only a dust continuum is seen with no gas, the object could still be a comet with low gas-to-dust ratio or with gas dominated by species not easily detected, but the evidence would be weaker. Another important clue is the presence of carbon monoxide or carbon dioxide-driven activity at large distances. Carbon monoxide can be detected in the radio if production is high enough. Carbon dioxide is more difficult from the ground because Earth's atmosphere absorbs in relevant bands, but space-based infrared instruments can detect it. If carbon monoxide or carbon dioxide dominate, that supports activity far from the Sun. It also changes expectations for acceleration, because gas species have different molecular masses and can produce different outflow speeds at given temperatures. Carbon monoxide, being lighter than carbon dioxide, can have higher thermal speeds. Water, being heavier than carbon monoxide, but still light, has its own behavior. However, the dominant factor in thrust is often the total mass loss and the geometry of emission, rather than small differences in molecular speed. Another compositional angle is the surface spectral class. Some asteroids show characteristic absorption features from silicates, such as olivine and pyroxene in the near-infrared. If such features are detected in an object without coma, that can indicate a rocky composition. If a coma is present, the dust can mask surface features. In some cases, the absence of certain features can still be informative, but the signal to noise and contamination make it difficult. Therefore, compositional conclusions are often stated as probabilities rather than certainties. Analysts also compare the object's colors and spectral slope to populations of known small bodies, such as outer solar system objects, long-period comets, and interstellar visitors like 1I Oumuamua and 2I Borisov. These comparisons are statistical. They ask whether the object's observed properties fall within the known distributions. If 3I Atlas has colors typical of long-period comets, that supports a comet interpretation. If it has unusual colors that could suggest different surface processing or composition. Yet unusual does not mean impossible. It means less common in the observed sample. The sample itself is biased because faint objects are hard to measure. Therefore, compositional interpretation must remain modest. A critical discipline in this section is avoiding overinterpretation of weak features. Sky subtraction errors can create artificial bumps. Telluric absorption by Earth's atmosphere can distort spectra if not corrected. Instrument sensitivity varies with wavelength. To claim a detection, observers require repeatability and consistency across exposures and nights. They also compare to spectra of calibration stars observed with the same setup. This ensures that instrumental effects are accounted for. When evidence is strong, composition becomes a stabilizing anchor for the physical narrative. If gas species characteristic of sublimation are detected, non-gravitational acceleration becomes easier to attribute to outgassing. If only dust is detected, fragmentation and dust-driven brightness changes become more central, and gas-driven thrust must be inferred indirectly. If neither dust nor gas is clearly detected and the object remains point, like then the case for significant non-gravitational effects weakens, and claims of responsiveness must be scrutinized more for measurement bias or for geometric misunderstanding. In the context of a title that suggests the object is responding to something, this section reframes the question as whether the object's emitted and reflected light reveals active chemistry and material release. Spectra can show whether sunlight is driving photochemical emissions. They can reveal which volatiles might be present. They can suggest whether activity is driven by water, by carbon-bearing species, or by other processes. They can also constrain whether the object's dust is typical of comets, or more like asteroid regolith. This inward move does not claim that composition alone resolves the motion questions. It establishes the material palette. It shows what the object is made of as far as light can tell. It provides the context for evaluating whether observed behavior is consistent with known materials responding to heat and sunlight, or whether the object would require unusual assumptions. The next inward step will return to dynamics, focusing on how planetary encounters and gravitational perturbations can amplify small differences into large trajectory changes. But here the emphasis stays on the molecules and grains that become visible when the object interacts with sunlight and begins to shed parts of itself into space. From composition and spectral clues, the analysis moves inward to the role of planetary encounters and gravitational perturbations, where the object's path can change in ways that appear sudden when projected onto the sky, even though the underlying mechanism is ordinary gravity acting through sensitive dynamics. In the solar system, an object's motion is never influenced by the sun alone. The planets, especially the giant planets, contribute gravitational forces that can alter trajectories. These forces are usually small compared to the sun's pull when the object is near the sun, but they can become important during close approaches. Even when an approach is not extremely close, the cumulative effect of planetary gravity can shift the timing and geometry of the object's path enough to change predictions. The essential feature is sensitivity. In orbital mechanics, small differences in initial conditions can grow over time, especially when an object passes through a region where the gravitational field varies strongly with position, such as near a planet. This is why orbit solutions are continually updated and why predictions can change noticeably as more data arrives. A planetary encounter is often described in terms of a flyby. In a flyby, the object passes near a planet, and its trajectory is deflected. In the planet's frame, the object approaches, swings around, and departs with nearly the same speed because gravity is conservative. In the sun-centered frame, the object's energy and direction can change because the planet is moving. This is the principle behind gravity assist maneuvers used by spacecraft. For a natural object, the effect is the same. The planet's motion allows an exchange of energy and angular momentum between the object and the planet's orbit. The planet's own orbit changes imperceptibly because the planet is massive, but the small object's orbit can change significantly. The magnitude of the change depends on the missed distance, the relative velocity, and the geometry of the approach. A closer approach produces a larger deflection. A slower relative speed allows gravity to act longer, also increasing deflection. The approach geometry determines whether the object gains or loses heliocentric energy. For an object like 3I, Atlas encounters with Jupiter are especially important because Jupiter's mass dominates planetary perturbations. Jupiter's gravitational sphere of influence is large, and many comets have their orbits strongly altered by Jupiter encounters. Even if an encounter is not extremely close, Jupiter can still change a comet's perihelion distance, inclination, and orbital period. The encounter can also shift the object from a bound orbit to an unbound orbit, or vice versa, in terms of barycentric classification, especially if the orbit was marginal to begin with. Therefore, classification of an object as interstellar or long period can be sensitive to how planetary perturbations are modeled and to the quality of the orbit before and after encounters. This sensitivity can create an appearance of the object changing its mind about where it is going when in fact the model is being refined, or the object is passing through a region of strong gravitational influence. In practical orbit determination, planetary perturbations are included by integrating the object's motion under the gravitational forces of the Sun and planets. This numerical integration uses planetary ephemerides, precise models of planetary positions over time. The integration predicts the object's future positions, which are compared to observations. When a planetary encounter is upcoming uncertainty in the orbit, before the encounter can map into much larger uncertainty after the encounter. This happens because the encounter acts like a magnifier. A small uncertainty in the incoming trajectory translates into a range of possible miss distances and approach angles, and each of those leads to a different deflection. Therefore, the post-encounter path can fan out dramatically. This is not a sign of non-physical behavior. It is a sign of sensitive dependence on initial conditions. Observers respond by concentrating observations before the encounter to reduce uncertainty. The more precisely the incoming trajectory is known, the more precisely the outcome of the encounter can be predicted. This is why a body may receive increased attention as it approaches a major planet. Another factor is that planets can also influence the apparent motion on the sky directly through Earth's own motion and through the geometry of the encounter. As the object approaches a planet, its velocity relative to the Sun can change, altering how it moves across the sky. This can produce apparent accelerations and direction changes. If observations are sparse, these changes can look like sudden kinks. With dense observations, they appear as smooth curvature consistent with gravity. The object itself does not need to apply thrust. It is being redirected by a moving gravitational field. Furthermore, the object's past history can be reconstructed by integrating its orbit backward in time. For comets, backward integration is uncertain because small non-gravitational forces and close encounters can make the past path sensitive. Still, for the time span of recent decades or centuries, it can often provide plausible histories. If the object has had previous Jupiter encounters, those encounters may have shaped its current trajectory, bringing it into the inner solar system from a more distant reservoir or altering its inclination. This is relevant because an object's apparent novelty can come from a recent orbital change rather than from being new to the solar system. For interstellar candidates, the key is the barycentric inbound velocity far from the planetary region. If the orbit remains hyperbolic when referenced to the barycenter at large distance that supports an interstellar origin. If the hyperbolicity is created mainly by a recent planetary encounter, the object may have been solar system bound before. Distinguishing these requires careful modeling and long arcs of data. In addition to major encounters, smaller perturbations accumulate over time. Saturn, Uranus, and Neptune can affect long-period comets. The combined effect of all planets can shift perihelion timing and sky position predictions by measurable amounts over months. For an object tracked over weeks, these effects are usually modest, but they can matter for precise ephemerides. Therefore, any discussion of trajectory changes must specify whether planetary perturbations have been fully included and whether the reference frame is heliocentric or barycentric. Another subtle effect is that planetary perturbations interact with non-gravitational forces. If outgassing changes the trajectory slightly before an encounter, it can change the missed distance enough to alter the encounter outcome. Because encounters are sensitive, a small non-gravitational acceleration upstream can have a larger downstream consequence. This can create a chain where modest outgassing produces a large change in long-term orbit through encounter amplification. This again can appear like a decisive alteration. The physics remains continuous. The magnification occurs because gravity near a planet maps small differences into larger differences in future trajectories. Therefore, when an object seems to shift its projected future path, analysts must examine where it is relative to any planetary encounters and whether the uncertainty mapping has changed. It is common for predicted close approach distances and post-encounter paths to be updated as new astrometry arrives. A prediction made early can differ from a prediction made later, not because the object has changed course, but because the uncertainty has been reduced, and the best fit orbit has shifted within that earlier uncertainty envelope. Observers sometimes summarize this as the object's trajectory being updated, which can be misheard as the object altering its trajectory. The discipline description distinguishes between model update and physical acceleration. In this section, the analysis emphasizes the mechanics of perturbations. Gravity assists and deflections are natural outcomes of passing near a moving planet. Uncertainty growth through encounters is a normal property of dynamical systems. Accurate pre-encounter tracking reduces this uncertainty. If 3I Atlas is associated with an upcoming encounter, the focus on that encounter can create a narrative of importance. But the physical reason is straightforward. The encounter will reshape the orbit and may determine where the object goes next and whether it remains observable. The presence of an encounter does not imply intention. It implies that a massive body is nearby in the object's path and will bend it. The implications for observation are practical. The object's ephemeris will become more sensitive. Predictions will need frequent updating. Recovery after the encounter may require searching a larger region if uncertainty is not reduced beforehand. For interpreting claims of responsiveness, this section provides a key caution. Apparent trajectory changes can result from gravitational perturbations and from the amplification of uncertainty near encounters. Without careful separation of these effects from genuine non-gravitational acceleration, one can mistake the natural consequences of orbital mechanics for unusual behavior. The next and final section will move inward to interpretation discipline itself, focusing on how human pattern recognition can attach intention to complex but physical motion, and how to keep conclusions bounded by measurement models and uncertainty. As the observational and physical layers tighten, the remaining work becomes a matter of interpretation discipline. The measurements describe changing sky positions, changing brightness, and sometimes changing morphology. Models translate those measurements into an orbit and uncertainty region, and when required, small additional forces. Each step adds structure, but each step also adds places where human expectation can drift away from what the data actually constrain. The phrase responding to something emerges easily because the mind is built to detect agency in irregular motion. When a point of light does not follow the simplest predicted line, or when it brightens in a burst, or when a coma changes shape between nights, it can feel as if the object is choosing. In the scientific workflow, the task is not to police language for its own sake, but to keep every claim anchored to a test that can separate ordinary causes from extraordinary ones. The first anchor is the distinction between an updated model and a changed physical path. Early in tracking the predicted future position is a probability cloud, not a single point. When new astrometry arrives, the best fit orbit can shift inside that cloud, and the new ephemeris can look different. This is not a mid-course correction by the object. It is a refinement of knowledge. A disciplined description states that the orbit solution updates as the observation arc extends and as uncertainties shrink. If the new measurements fall within the prior uncertainty envelope, the dataset behaves as expected. Apparent changes in predicted outcomes are then an artifact of earlier uncertainty, not evidence of new forces. The second anchor is the separation of measurement effects from physical effects. Astrometry depends on locating the center of light. When an object develops a coma, the center of light can drift away from the nucleus due to asymmetry in dust and gas distribution. When the background field is crowded, centroiding can be biased. When seeing worsens, profiles broaden and centroids become noisier. When different observatories contribute data, small systematic offsets between instruments and catalogs can appear. These effects can create residual patterns that resemble acceleration. The test is to check whether the residuals persist across independent datasets, whether they correlate with observing conditions, and whether they survive conservative reweighting and outlier rejection. If an apparent deviation vanishes when coma-affected points are down-weighted, the deviation is more consistent with measurement bias than with a real change in the object's motion. If a deviation persists in high-quality data and grows coherently over time, the case for a physical effect strengthens. The third anchor is the hierarchy of physical explanations. Gravity comes first, including planetary perturbations and the correct reference frame. Encounter sensitivity can amplify small differences and can widen post-encounter prediction clouds. If the object approaches a major planet, the mapping from incoming uncertainty to outgoing uncertainty can be large and ephemeris changes can look dramatic. Within gravity, there is also the difference between heliocentric and barycentric descriptions. A marginal classification can shift slightly when the reference frame changes. A disciplined approach makes these transformations explicit and avoids treating small numerical differences as separate realities. If gravity alone fits the data within realistic errors, additional forces are not required. If gravity does not fit, the next layer is sunlight-driven non-gravitational acceleration from outgassing. This layer is supported when activity indicators appear an extended profile, a dust tail brightness trends beyond geometric expectations, and spectral evidence for gas. Even without strong gas detections, dust-driven activity can still imply gas flow, because dust needs a lifting mechanism. When a non-gravitational term is fit, the test is whether it improves residuals in a stable way across data subsets, and whether the inferred magnitude is consistent with plausible mass loss, given the object's size bounds and observed coma brightness. Variable acceleration then becomes a question of rotation, modulation, seasonal illumination, thermal lag, and evolving vents, all of which are known to produce changing thrust without requiring any external signal beyond sunlight and the object's own structure. The next layer is fragmentation and dust dynamics, where sudden brightening and changes in morphology can occur when internal stresses exceed strength. Fragmentation can also alter which component is being tracked, changing the apparent motion. This can be tested by high-resolution imaging that resolves multiple condensations, by monitoring whether the brightness peak shifts, and by modeling the dust tail as a time-integrated record of emission. In this hierarchy, the language of responsiveness is replaced by a sequence of testable mechanisms. Each mechanism makes specific predictions. Measurement bias predicts correlations with seeing background and instrument. Gravity predicts smooth curvature and encounter-dependent sensitivity. Outgassing predicts correlations with heliocentric distance illumination, geometry, brightness, and often a preferred direction relative to the Sun. Rotation-driven jets predict periodicity and morphology evolution tied to a rotation period. Thermal lag predicts time shifts between peak heating and peak activity. Fragmentation predicts sudden photometric changes with morphological evidence and an evolving dust field. The fourth anchor is scale. Non-gravitational accelerations that matter for orbit prediction can still be tiny compared to solar gravity. Their influence becomes visible because it accumulates, not because it overwhelms. This keeps interpretation grounded. A small persistent acceleration can shift predicted sky positions enough to matter for recovery while still being consistent with modest mass loss. In the same way, a small upstream difference in trajectory before a planetary encounter can produce a larger downstream difference after the encounter. Sensitivity does not require strong forces. It requires a system where small differences map into large, later separations. The fifth anchor is the constraint of available information. Brightness-based size bounds depend on albedo assumptions and on whether a coma contributes. Composition inferences depend on signal-to-noise and on atmospheric correction. Gas production estimates depend on wavelength coverage and sensitivity. A disciplined approach states what is known and what remains uncertain. It does not fill gaps with intention. It also does not treat uncertainty as a failure. Uncertainty is the correct description when the data allow multiple compatible paths or multiple compatible physical states. This is especially important for rare objects where there are few comparators and where selection biases shape what is detectable. A final anchor is that pattern seeking can be redirected into model checking rather than narrative. If the object seems to change course, the first check is whether the change lies outside the prior uncertainty region. If it does, the next check is whether it coincides with a change in data quality or observational geometry. If it survives those checks, the next check is whether activity indicators rise at the same time. If they do, a non-gravitational model can be fit and tested. If activity indicators do not rise, alternative explanations are considered, such as catalog biases, misassociation of detections, or unmodeled gravitational influences. At each stage, the claim is bounded by a calculation or by an observation that can be repeated. In this way, the same dataset can support careful excitement about a challenging analysis problem without drifting into conclusions that the measurements cannot justify. 3I Atlas remains at the most fundamental level a small body moving through a gravitational field while exchanging energy with sunlight and possibly exchanging momentum with escaping material. The appearance of responsiveness is a natural outcome when observers compress a complex chain of measurement updates, uncertainty, shrinkage, activity, onset, and encounter sensitivity into a single phrase. The disciplined approach expands that phrase back into the chain and tests each link. When the chain holds, the behavior becomes understandable in terms of known mechanisms. When the chain fails, the failure is located precisely as a mismatch between predicted and observed positions beyond realistic error sustained across independent observations with no adequate physical mechanism among those already established. Only at that point does the question shift from interpretation to the possibility of a new ingredient. Until then, the most faithful description remains close to what the sky and the instruments actually record: timed angles, changing light, and the gradual tightening of a path through space under forces that are small, layered, and measurable. In the final moments of this account, the pace stays slow and steady. The telescopes continue their patient work. Images accumulate. Points of light are measured against stars whose positions are known with care. The orbit is refined by repetition and uncertainty narrows by degrees. If a faint haze surrounds the point, it is traced without haste, its shape compared from night to night. If the point brightens, the change is placed beside the geometry of distance and sunlight, and beside the physics of heat moving through porous dust. If residuals grow, they are tested against catalogs against seeing against the shifting line of sight from a rotating Earth. If a small persistent push is required, it is modeled as momentum carried away by gas and dust, shaped by rotation and by the uneven face of a nucleus that warms and cools. If the path bends near a planet, the bend is treated as gravity acting through a moving mass with sensitivity that magnifies small differences. The object remains a natural body, and its apparent complexity remains a combination of changing illumination, changing structure, and changing viewpoint, all recorded through methods designed to keep measurement separate from story. As the night sky turns, the record grows quieter in the mind, returning to what can be counted and compared, and to what can remain unknown without pressure to resolve it.